working only for the conference? Okay, now it's working. Okay, good afternoon. We are about to start the real-time and scheduling micro conference. This year we put together these two conferences that we used to have separated, and it was on benefit because we have like a nice schedule today involving these two technologies that at the end we are all the same people. Uh, we would like to thank our sponsors, and the microconference will run as usual. We can make questions anytime. We have the microphones, and I always speak on a microphone so people in the room can listen to it. And these microphones, they are turned off by default. So when you get one, just wait a little bit so that they can turn it off or turn it on before speaking. So people in the room, in the BBB can listen to the questions and make them connected with us as well. And we'll just do one small change in the schedule. Frederick came with a problem that is in the interest of this community. So I will shorten my presentation, the first presentation, and I'll give a slot for Frederick. This should not impact our schedule overall. And yeah, let's start with mine. So this is more a conversation to get feedback of what is more important for us to continue doing on RTLA. The the RTLA is a meta tool that includes a set of commands that we have to analyze the properties of the real-time Linux. It was presented as a sorry? Then you need to talk with people in the audio. All the previous one was like this. It's not. So the RTLA, I presented it as a proof of concept last year at the Plumbers, and it made its way to the kernel. The idea is to get together a good interface or an easy to use interface for the tracers to the analysis of latencies on the real-time kernel, like the timer lot or the OS noise, and put together a more digestible output. In other words, the idea of these tracers is to get the knowledge of an expert analyzing the traces of the kernel and put it in an interface that everybody can use. And the importance of this is that with the merge of the parameter RT around the corner, we'll probably have more people interested on trying and debugging the real-time kernel, because the real-time kernel will be everybody's problem, not only a small community. And so just to have an idea, this tool here, it's timerlat top, and it measures the latency of the thread and IRQ in the timer, and it reports it. But it also helps to collect the trace and provide trace output. I'll show more of that later. And another tool is the OS noise top that I presented this morning. And and so the timer lot, it works well, but it has one limitation, which is it Steven here? Okay, this was a question for Steve. So when the way that the timer lot tracer works is that it schedules a timer in the future. When the IRQ raises, it prints an IRQ latency, and then it wakes up a thread and prints the thread latency. Similar to what cyclic test does, but including more information from the IRQ context. And now what happens is that we have in kernel, we have sorry, we have these events that we collect via trace interface. And these events are ftrace events. They are not trace points. And one of the problems is that you see, it's like a function graph tracer. And one of the problems is that when you have like very large systems, like more than 100 CPUs, and with a period of 100, I say nanoseconds, but microseconds, we start overflowing the trace buffer, and we cannot make it up to collect and print the data on OS not on TimerLapse. And on OS noise tracer, we don't have this problem because we can use the histograms features on the trace. And so we do all the histograms in kernel. And we cannot do histograms here because these are not trace points. These are trace are outputs of a tracer. And if you look in the ftrace interface, we do not have like the the trigger option here. So I cannot enable histograms. And this would be something that I need to discuss with Steven. But I will do it short to give time to Frederick to discuss about it. If you have interest on this part of infrastructure on trace and have time to help us on this, um, yeah, ping me and I can help on that. That's something that we need to fix. Another thing of interest is try to integrate the hardware lat tracer with RTLA. So we can do together the timer lat tracer that is like cyclic test, but reserve a CPU for us to collect the hardware noise. And
even more than one CPU for the SMI thing, like the hardware lot, because I've seen that even, I mean, there might be something that's triggered when you run the SMI detection on multiple CPUs.
Yeah.
Just make it, I don't know, general. The one
Yeah,
can specify.
that's possible.
Yeah.
So the idea would be to have like the timer lat tracer working together with hardware lat, so we can detect latencies caused by the operating system and by the hardware, because we usually see those two things together many times, like when debugging customers at Red Hat, and having both together can save us time. Instead of running two tools in different times, we can have a tool reporting it. And the idea of the tool is to actually do this kind of automation. Another thing that I would like to add to TimerLat is supporting trace.dat files, which are files from trace command. Now what happens is that when TimerLat is tracing and we find a latency, it saves the trace output to a file. But this is just a text file. It's easy to read, but I cannot do more automation that I can do with trace.dat. For example, with support of a trace.dat file, we'll be able to run multiple trace instances and run the timerlat, which is a tracer, and the function tracer on another CPU, and merge them together. And that's another feature that we plan to add to timerlat. And it shouldn't be hard. And and finally, all this tooling was created based on the motivation of the RTSL, which is the tool that I created to get the formally proof scheduling latency, monitoring the events of the preemption model. And let's say that tool was not merged yet here on RTLA, but the timerlat and OS noise are already using part of that infrastructure. And so I say this internally at Red Hat that that tracer was La Ferrari, while this the timerlat is the Fiat 500. La Ferrari was the nice proof of concept, but at the end of the day, we all use Fiat 500 to go to work, at least in Italy. So it's more useful for now. And another problem of the RTSL is that it will depend on the usage of trace points that are not always enabled, like the preempt disable and preempt enable. And there are some problems that we report on the WIP monitor on RV. But once that gets figured out, that problems with the trace points, my idea is to add the RTSL inside the timer lot. But that's it. This should be a longer presentation, but I'm shortening it to give space to Frederick for him to discuss the SoftIRQ issues. If you have interest on RTLA, or if you want to discuss some of these topics, please ping me or discuss it in the Trace Devel mailing list. And all the help is welcome with RTLA. There are a lot of features to be added, and we'll be glad to integrate them. And thanks, Frederick. Oh,
There was a question for you. There was a question for you on the
okay.
on the
Yeah,
chat.
okay.
Using timer can I target only specific CPUs?
Yes, we can target the CPU set in the. We can use. The question was, can I target just some CPUs on the system using Timerlot? And yes, you can mention the CPUs that you want to use. And with RTLA Timerlot, you can just say Timerlot-C the CPUs, and if you want to measure those CPUs.
Does it work? Yeah. Okay. Yeah, sorry. So this is going to be a very short talk. Just to remind about patch set I posted a few years ago. That was about, because you all forgot, right? So this patch set was about per vector masking. So currently, when SoftIRQs are executing, they one vector serviced cannot be preempted by the servicing of another SoftIRQ vector. And SoftIRQ disabled regions cannot be interrupted by the SoftIRQ servicing. Oh, right? Okay, so I introduced a few functions to be able to disable only specific vectors instead of disabling all of them at the same time. So that, for example, if a given code chunk disables the networking receive SoftIRQs, timer SoftIRQ can interrupt that region and execute on top of it. This also works for spinlock BH and related SoftIRQ disablement functions. And one thing that this patch set wouldn't do yet was per vector unmasking. So this is the reverse. When we service a SoftIRQ, this disable all SoftIRQs. So one thing that we could do is to enable a specific set of vectors when we execute a SoftIRQ callback, if we know that this is safe. Like, for example, if I execute a timer callback, and I know that this timer callback is safe enough to be interrupted by another SoftIRQ vector like net receive or net transmit or whatever, then I can enable temporarily SoftIRQs. So I was wondering if such a patch set would be welcome nowadays. I think so, but I'm not sure. So what's the general opinion? At the time I posted the patch set, it was only useful for real time. Nowadays, I don't know if it might be useful outside real time. Anyway, so input on that? One, yep.
It looks oddly similar to what is being done for signals in user space. And the design they do for that is a specific signal handler is associated with a mask of the signal that needs to be masked or not.
Yep.
So maybe rather than having those disable and enable local and things like that, maybe you could start by having in the definition of the SoftIRQ handler a mask associated with it. So it would be clear that, okay, yes, this handler allows enabling those and those are masked out, rather than starting to play games kind of locally disabling and everything. I mean, you make it clear that this handler needs to support it.
So you mean for each callback, there would be a specific mask? Yeah, but there are tons of these.
Yes, but you start by keeping the old behavior, and then, I mean, as you specialize and review code of a few, then, I mean, you could, okay, start enabling some of the other SoftIRQ so they could nest.
Yeah, so even more fine-grained, right,
Uh,
than what I'm proposing.
well, it's, I mean, associating the callback of the SoftIRQ with the definition of what it supports as nesting, rather than adding in the code some regions that kind of, oh yes, this piece is good to go and not.
Yeah.
Yeah.
Okay. I think Sebastian has a question.
Do we?
So back then, as you posted the first version, I was test driving in RT, and I have no idea what you implemented back then for unmasking specifically, but I remember I was using it for a few hours, and it was like perfect. And then at some point, the timer kicked in and used the same SoftIRQ that we didn't see to begin with. And then you locked up extensions, triggered a warning to make us
Yeah.
aware of the error.
Yeah.
Um,
Yeah, there was a lock depth detection based on locking, which would detect if you abusively enable the vector and detect it if another vector that had been enabled could interrupt the current one and
Exactly.
explode, deadlock.
Yes. So from our T point of view, we wouldn't care at all because we would never deadlock. We would still go through. But for mainline, this is like necessary because otherwise you will deadlock mainline wise.
Yeah.
What my point is that it's kind of difficult to see, especially networking, where the call chains are very deep.
Right.
We never saw the timer to begin with, right? So this is kind of nasty. So it looks complex to begin with.
Yeah, it is.
So I have no idea how many fans we get for that. Because networking has a lot of precipue data that is protected only with BH disable. Not all of them are documented as in we disable here because this is the data we protect. Often they rely on a spin lock that also disables, and this is it.
Yeah.
And they also rely that we do this here and the timer as well, but never can run at the same time.
Yeah, unfortunately, that cannot be detected with lock depth or things like that. Yeah.
Yeah. So as much as I'm a fan of that one, it looks pretty complex for that.
It is. Yeah.
Also, I don't remember from the cover letter if you had like some numbers showing numbers from use cases where this really helped. Like if you had that, I was curious.
Well, I did really some very light testing, and I did not really measure anything. But there were a lot of call sites, especially networking, I guess, where the SoftIRQ can last for a long time, and then it could be useful, I guess.
Against timers.
Yeah, right. Retain timers from executing for a long time. Yeah. It was deemed to be short anyway, so.
Next, right? Yeah.
CPU. Per CPU. Undocumented.
You can, okay. Ricardo, why don't you try?
Yes, can you hear me, guys?
This is Ricardo Neri.
Hi.
We both work at Intel, and we're going to talk about we're going to talk about hybrid scheduling on Intel in general. It's not EAS specific as the program says, but we can talk about EAS in there as well, and we'll talk about why that's good and bad on this particular piece of hardware. Let's see. So I'll start and I'll go through sort of how the hardware works, so we all are on the same page there. And Ricardo will talk more about the scheduling, since he's the one cutting most of the code in this area and can do a better job than I. So this kind of diagram is meant to show what we call a 2+8 system. So there's 2 P cores and there's 8 E cores, formerly known as atoms. Important to realize that on this chip, this is a picture of an Alder Lake, which is shipping today. Maybe there's some Alder Lake laptops. Raise your hand if you have an Alder Lake laptop. Nobody. Go buy some. There's SMT on the P cores, which is pretty important from a scheduling point of view. So it's important to realize the bottom line is the same instructions run on all processors. So not every concept works that way, but that's how our products work and will work for the foreseeable future. Here we're depicting blue as a completely idle CPU, and the orange boxes are supposed to be work. Okay, and there's a run queue on one of them, the other one's no run queue. So this is sort of the decoder for what comes next. So if you look back in 4.9, where before we enabled ITMT, which is for Intel Turbo Boost Max technology, also known as ITBM, 2 acronyms for the same phrase. Linux treated all the CPUs as the same on IA, and so it's sort of random how work would be placed on different CPUs, though we did know about HT. You'd use the E cores sometimes and the P cores other times. And so your variability in performance could be quite different. And I must highlight, the instruction set's the same, but the performance can vary quite a lot, and we'll talk about more of that in a second. And so in 4.10, we enabled ITMT, which enables the ASIM packing in the scheduler. And so we would prefer the P cores over the E cores. Unfortunately, the way that code worked on this piece of hardware, it also preferred the P core siblings, which is generally a bad idea. You really want to use a dedicated E core rather than a busy HT sibling. So basically, we fixed the, and that's how you disable it if you're burdened with a kernel of that age. And we fixed that in 5.16. So we have task placement E core, P core, E core, P core, HT sibling. Pretty straightforward. Yep. Okay. And so the way this works is HWP in the hardware informs the Intel P-state driver, which hooks into the ASIM packing ITMT in the scheduler. And that, all it does is in the idle load balancer. Doesn't touch anything else, doesn't touch the wake up path or the periodic load balancer. Okay. Okay, so starts to get more interesting here. Remember, I said that the reason the boxes were bigger, the P cores are faster than the E cores. They're not just faster in that they can go at a higher frequency, they actually can get more work done per cycle. So this is an IPC ratio of 1.27. I think I actually showed in the Yogini talk yesterday a picture of this being measured, where you could see the IPC, and then when the 2 siblings are busy, the IPC of the P core actually drops below that of a dedicated E core. This is for a nominal instruction mix. What is that nominal instruction mix, right? The answer is it's integer code, but we'll talk about that more in a second. Here, a new feature that comes along with this piece of hardware is called hardware feedback interface. It's been documented for some time in the SDM. And it gives a performance and efficiency score. We're focusing on performance for today. And what it does here is this 56, and well, first look at the what's supposed to be green part down there is the E-cores. That 3.0 stands for 3 gigahertz. So we sort of normalized to 3 gigahertz. So performance and frequency are the same. And for the P-cores, we remember that 127 from the previous foil. We multiply that by the frequency, and we get 56. So it's sort of like it would be a 5.6 gigahertz E-core is what the P-core is, right? And so that's where the numbers in this table come from. And what this table does, we already knew from HWP, interface for hardware P states, these exact same performance numbers. But the thing about this table is, at least in architecture, it can change at runtime if conditions change. It also gives us efficiency score, and that could also change at runtime. This table can be updated dynamically. Every CPU maps to a row, and as you can see, some of the rows are shared. Okay, so that 127 was an oversimplification. So enter a feature called, what's now called, what do they call it? Intel Thread Director, ITD, yes, sorry, I should have put it on the slide. Intel Thread Director adds the notion of, oh, not all ICEs are created equal. So sometimes if you're running SSE, or say if you're doing system calls or kernel code, it's probably that 127 is actually right in the ballpark. But if you're running AVX code, it's maybe 1.5 times faster. If you're running VNNI, it might be 2 times faster or more. If you're running a pause loop, who cares where you run? It's the same, right? There's this concept of these ICEs are examples. The classes are what the kernel looks at. It looks at the table. It doesn't actually say, oh, you are AVX. It just says, you're class 1, and I know what to do with class 1. I'm just labeling AVX so that you know what it means, but the kernel doesn't care. And so what we do in ITD is we expose, instead of one 1.27x multiplier, we expose 4 classes, performance 0, 1, 2, and 3. So say that last one was the pause loop, and you can see that 4.4, that's 1.0 times 4.4 gigahertz, right? So that's the place where the performance was a wash, and you just see the frequency difference. And the other ones, you can see the 2.0 is, and this is how the kernel can know that if it's a really good idea, for example, to run VNNI on a P core versus an E core when there's a choice, okay? Because you can double the performance if you choose right. It's not just frequency, it's what you're running there. And that's a pretty cool feature. The way this is implemented is at any given time, you can read this feedback register, and it says what ISA class has been running recently. And then, of course, when we context switch, there's an H reset instruction that says, oh, forget all what was running over there and start analyzing for the new task, so that we can give tasks an identity, which we're putting in the class, and remembering it for the next time we want to schedule that guy, where do we want to put him?
And now let's see how that looks in the implementation in the scheduler. As Len was saying previously, what we do today is to use HWP to determine what are the maximum frequencies of each individual core on the system, and we feed that into the scheduler using ITMT, and that enables the async packing flag in the scheduling domains. Today it is done in the SMT domains and the MC domains. But the new things are the thread boxes, Intel Thread Director as Len described it. And our proposal is to introduce the concept of classes of tasks in the scheduler, and that is implemented adding a new member to task struct, which essentially is going to be populated by, in our case, with Intel Thread Director with the register that Len described, but it can be implemented in an architecture agnostic way, whatever method architecture decides to implement that. And then our idea for use classes of tasks in the scheduler is to use it in addition to whatever the scheduler is doing today when balancing load, to decide, for instance, in between two otherwise identical scheduling groups or two identical run queues, and use the classes of tasks that are running in each of these run queues and break a tie between two identical choices that we will have when doing load balancing. What we see here is a depiction of async packing load balancing. What that happens it only happens when in the idle load balancer. So what we see here is the destination CPU is idle, or it is going to be idle soon, and it wants now to pull a task from lower priority CPUs. So if you see here, the P cores have higher priority and all of the E cores have the same priority. So today, either of these BC E cores are equally good choices, but then we can look at what is running at these CPUs. We can observe here that we don't have nothing waiting to run on them. All that we have is the current task running on them. And then the load balancer in this case will check what is the current task on these run queues and decide, okay, this is a class 2 task and the other one is a class 1 task. And then it will look for what we call the performance scores for classes, and it will see that class 2 has it will run with a higher performance or a higher IPC if it was to be placed on the destination CPU. And then it will break this tie and pull the task 2 into the destination CPU. And this is the other case in which we have we observe here that we have the two SMT siblings. One is only one SMT sibling BC, other one is the two siblings are BC. And then the destination CPU here, it is a lower priority CPU. Again, this happens in the idle load balancer. And we want to decide what would be the best task that we could pull onto the destination CPU. And the intention here is to, since these are lower priority CPUs, we want to leave the task that will run with the, yep.
There is actually a question from Giovanni online. I read to you. Can you confirm the hardware Intel thread director is aware of tasks? I'd expect that from the CPU point of view. The cycle is a cycle. How can it differentiate tasks?
This is what Len was describing a minute ago, in which the hardware has resources to monitor the instruction stream, and it will see what the current task is doing, and it will write the classification on the class register. And then when the scheduler is doing when the system is entering the timer tick, it will read that register and write unassociated with the currently running task.
Basically like this. So the hardware is doing the work, we just read the answer. So in theory, you could do this in software, but we'd have to read a whole bunch of counters to analyze what's going on, and that would be a heck of a tax in the kernel. So the hardware does that for us. This gives us the answer in this register. We read it and say, oh, great, it's class 2. And then we read it on user clock tick. That's when we just record it. That's all we got to do.
Yeah. When there is a user tick, we are obviously running the current task, and we can associate the answer with that
So
task.
it's sampled. Yeah, it's sampled at user tick.
So I was saying, so the intention here is that we want to leave the bigger CPU with the higher priority CPU to the task that will benefit the most. And in this case, we have two choices between two equally otherwise identical run queues, which is 2-on-1, and we know from reading the performance information that the hardware provides to the scheduler, and we see that it will be better if we left the task labeled as 2 here to the big CPU, and then the CPU doing the destination CPU in that case will pull task number 1 onto itself.
We should probably add that the patch series that Ricardo sent last week does this.
Yes, we posted last
Does
week
these
on Friday.
Does these 2 cases. And so now we're going to talk about some cases that the patch series does not do, and we're interested to know if people think it's a good idea or a bad idea.
I think I find a lot of similarities between this and like the hints that people are talking about giving tasks, you know, that require low latency, for example. I know this is happening in the idle load balancer, but generally in the scheduler, right, if you want to give something low latency, you might want to give it like an idle CPU. In this case, you're getting the hint from the hardware. Yeah, what I've heard is people, you know, talking about giving this hint from user space as well. But yeah, so I was kind of thinking through these similarities and if there's any opportunity to kind of have common code, but maybe get the hints from different places.
So 2 things. One, it's interesting. I hadn't thought of the possibility of the user space being able to override that. I mean, for debugging, we can do that. But, you know, we come at this from the hardware point of view, which is, hey, this is a great feature. Let's how to expose it. But, you know, maybe there's a possibility that the user might say, treat me this way. That's, you know, that's something we hadn't thought of.
Yeah.
With respect to acting on it like you might act on a hint for latency, I think the problem would be that you may want to do different things. There's a couple of more scenarios than just this. Basically, what we've shown here is the ISA difference says when basically everybody wants to run on a P core. The question is who's going to benefit the most running on the P core? That's what we're trying to discover and expose here. I don't know if we'd take the same actions as on a latency hint. I don't know.
If you could combine that hardware info with other info as well, I mean.
Maybe.
Yeah, that is a good point. Here, we are talking about a system that is fully busy in the sense that each CPU has 1 task to run. And the scenario you are describing, I think, is when you have a CPU sitting idle and you want to use them first, right? Or prefer to place a task there.
That was my question. You're always looking for an idle CPU?
No, we have more cases.
Okay.
Yeah.
Because the point is that when it's idle, typically you want to look for a task to move. So you can probably take your
Hold that thought for a second. We have the non-idle.
Yeah, that was the next point. Then when you're not idle, you have to compare the load. And in this case, how you will mix the load, CPU load, task load with this value, which is quite orthogonal.
Yeah, the next 3 slides touch on that.
Is a follow-up question to Joel's point by Youssef. Along that line, can the code class be detected by the compiler?
It could, yes. And that would be similar
to.
to.
Repeat the question. I don't know if everybody heard it.
If the class of a task can be detected by the compiler and give it to.
Yeah,
the
good
kernel.
question. Good question. Of course, if it did, we wouldn't need this hardware feature, you know, if everybody did that. Yeah, but yeah, in theory, sure. Yeah.
Yes, I guess that there a need to implement the interfaces for the user space that communicated.
But honestly, I have to say the hardware feature is better. And the reason is because those classes I gave you are an example. And you could compile something and then run on a different chip, and the classes are totally different. For example, VNNI might be twice as fast on a P core on this chip, but it might be 5 times or half as fast on this chip. And or it may detect the classes completely differently. And it might be, I don't care about VNI, now I care about something else because VNI runs at the same speed as AVX2.
Yeah, and also Mel Gorman commented that the compiler could detect that certain instructions are used, but not the relative hotness at a point of time.
Exactly,
Yeah,
exactly.
that's another-
And the thing about that table, the register and the table I showed, that table is actually the definition of what comes out of the register. And you can't know that at compile time. You can only know that at runtime.
And there is a Shrieker. You raise the hand remotely if you want. If you have a question, please ask.
Yeah, so I had two
Adding to
questions.
that, it is also possible that during the lifetime of the task, it changes its behavior,
Right.
and that will change the
Yeah.
classification, and yeah, it would need to be placed somewhere else.
Good question.
And yeah, the last two slides were showing what to do when a CPU is going to be idle, and we were doing an idle balance or a nearly idle balance. And now what we have here is what will happen if we had two CPUs running busy, and we will do the load balancing periodically. And in this case, what will need to happen, again, we compare the relative goodness of each task running on each of these CPUs, and we will see what combination will give us the highest throughput. And there is precedent for this today when in the NUMA scheduler, uh, tasks can be swapped if they are found to be if they are found in the wrong node, and the scheduler will the scheduler will stop the two CPUs, swap the task, and continue the execution. We want to reuse that code. As Aslen said, this is not, we haven't posted this code, but what we want to use is to leverage that code, stop two CPUs, and swap the task so that with that combination gives us the maximized throughput. And again, in this case, we will need to do that because we don't have anything waiting to run. So we will have to swap the tasks that are currently running.
So this is, we were talking about stop machine earlier in the day. This is where we would use that here.
Yep.
Yeah, we had the remote. Yeah, Shrikar, if you can try again to speak.
Yeah, I had two questions. One is do we have a numbering thing for the P course and the E course? As in the E course would always follow the P course, or can the P course be interleaved? The second question is, have you thought about the case where the E course can also have threads? Like, what if the capacity of P core and E core could be different, but both of them might have threads. Have you thought of those cases also?
So let me start with the numbering one. So I think you mean like here is CPU 0. This one is, you mean like Linux CPU numbers? Is that what you're
Yes.
referring to? Okay,
Right,
yeah.
right.
So Linux gets assigned CPU numbers based on the order that CPUs appear in the APIC table. And that's a convention in the BIOS. And the convention on Alder Lake would be, I think I showed it yesterday in the Yogini presentation. Today it's CPU 0 is a P core, CPU 1 is its sibling, CPU 2 is a P core, sibling 3, and so forth. And then when you get to 3 through however many of all the E cores come last. That's the current convention. But a BIOS could scramble that on you. So you can't technically, my tools assume this convention because they've never seen anything else, but technically it could get scrambled. And I'm sorry, what was the second question?
So in future, can there be a E cores also having SMT, but the P core and the E core have still has some performance difference? Like, right now your E cores are not SMT, right?
Right. I mean, I don't speak for the hardware guys, but I know of no proposal to add SMT to E cores. And the security guys would cheer at me saying that. Yeah.
Yeah. Okay.
So let me catch up to where we were. think we were on the live exchange.
Yep.
We're done with live exchange?
Yeah, but can you go back one
Okay.
slide? And yeah, I forgot to mention here the reason why we want to offload one of the tasks of the SMT of one of the SMT siblings of a P core. And the reason is that if you have two tasks running concurrently, they will be sharing CPU resources. So even if you have a high performance task, it will be slowed down, quote unquote, by the other task, which is sharing the whole core.
And we showed a picture of this yesterday, where when we added the very end of the pyramid, we added the SMT siblings, and you could saw how the original guy got almost cut in half.
Yeah, so I was saying that this is the case in which we have no wrong queues, and the only thing that we can swap here is the two tasks that are currently running, which brings the need of having to stop the CPUs.
And I should mention that we have this running. It's just not in the patch set. This works.
Yes. And here are the things that we are thinking on implementing, and yeah, but we would like to know what you guys think of them. These are the cases in which there is a tasks waiting to run that are runnable. And again, we want to use classes of tasks to break ties between otherwise identical run queues. The case that we have here is that we have the load balancer has identified that there are two run queues that has identical load, and what we want to do is to maybe prefer the run queue that has the runnable tasks that have a that will have higher performance if placed on the bigger CPU. So in this case, what we will do, instead of pulling the task number 1 onto the destination CPU, we will pulling task number 2, which is similar to what we saw in the previous slide, but in this case, we will not be stopping the CPU. We will just pick it from the run queue.
If you're going to move it to the SMT sibling, why don't you move the other task? One that may not benefit as much by running on the single core.
Yeah, in this, so if I understand the question, why will you want to increase the run queue of the SMT sibling?
No. What I'm saying is, instead of moving task number 2, which would have to share the core, why not the other task that's sitting on that run queue, and then that way 2 gets the full benefit. When you just pointed out that if 2 were to go onto that shared core, its performance would be lower as compared to holding the entire E-core.
Yes, that is true. But also in that case, 1 will have lower performance. Yeah, it will be 2 and 1 will be sharing the CPU with whatever is running on the sibling.
Sorry. Let me. So let's.
Why are we moving him at all? Is that
No. Why aren't we moving the other task on that E-core? Right, the 2 tasks causing the imbalance.
It's just
right?
an example.
Okay.
You mean we could have moved this guy instead of that guy?
Yes.
Yeah, it doesn't matter. We can search through and see 1s and 2s and pick the class.
But you would want to pick the task that.
Oh, would we pick from the front? I think today we pick from the back, just in the.
Yeah, we start.
That's how the load balancer works today.
Right.
Today it's just blind to class. What we would just say is we make it not
pick the
blind.
one that has the lowest class, I mean, essentially what I'm trying to say is the task that comes up with class getting only 1x improvement as opposed to say 1.27 or 1.5 or 2. You would want that task to stay on the E-core as opposed to it sharing resources on the P-core.
Okay, so the concept of the load balancer is that number 2, no matter what his class is, getting a chance to run even on an HT sibling is better than waiting on the back of the queue for the E-core. Okay, so if you look at it as a time slices over time point of view, the whole concept of the load balancer, independent of classes, is that he'll get to run sooner, even if it's on a slower CPU. That's better than not running at all. So we're sort of basically tweaking that algorithm. We're not replacing that. That's how it works today.
Yeah, we are evening out the load between all the run queues, and the question is, which run queue will benefit
So
the most?
this is a crude picture, but basically if we did nothing today, the things labeled 1 or 2 one of them would be chosen arbitrarily today. Even if the CPUs were the same, different, doesn't make any difference. Okay. Q2, all right. Oh, they can't hear you online without a mic. Here's one.
Here.
So what I'm trying to say is let's go back and say our original choice was between Q1 and Q2.
Yeah.
And we pick Q2 for whatever reason. Now in Q2, shouldn't we be picking the task that has the
Inside
least-
Q2, not necessarily the back, but yes,
Yes.
yes, I agree. And I believe that's what we do.
We will be picking the one that will benefit the most on running on the.
So we could have
P4.
gone another slide where 1 and 2 are in the same queue, and we would have chosen 2 because he's different, because of his class. Yes.
Right, okay.
Yeah.
And how do you integrate that? Right now, in this case, we are comparing the load balance in order to share the time fairly between all the tasks. So how do you use this new input with the load to say, okay, if I move the task,
To break a tie.
yeah,
Yeah, only when there's a tie.
okay, but I mean, are you sure that you will not create an imbalance between all the tasks and the time sharing?
The time sharing fairness between CPUs is already so horribly broken. How could
No.
we make it worse?
No,
You don't think it's broken?
not
Okay,
that
we'll
much.
need another session on that one.
Yeah. It's all the purpose of the CFS and the load balance is to make a fair distribution of the CPU time between all the tasks. Here, what you're saying is that we don't care about time sharing. We want to use the metric.
So, okay,
I mean, you need to
you've
take
touched
both. You
upon
can
an important topic, okay? So let's just say Ricardo and I are different tasks. Say he's a VNNI task and I'm an integer task.
Yeah.
And we both get to run, if the CPUs are all the same, then it's all about, did we both get a time quantum? Did we both get a fair share? But if we can double the aggregate throughput by having me run on this CPU and him run on that CPU, and we both get the same time quantum, then that's good, right?
But
Right.
how do you ensure that you are not breaking? That's my point.
Well, right now, we're going to pull this task anyway.
Yeah.
So if we can't break it, it would have had to have been broken already. No, we're only doing this if we were going to pull it anyway. Okay? That's why the picture is drawn as it is. There's an imbalance here already. The periodic load balancer is already balancing this queue for time sharing.
No.
No, that's the scenario I'm talking about.
Okay, so you have an imbalance.
Yeah.
But in the case, typically, if you're there, and let's say that on your SMT CPU,
You're saying if I pull an arbitrary guy out of the queue, then I could
no,
break,
even that,
do that
look
wrong.
at this use case, let's say that on the SMT thread, the one that is a load, the load is 3 times higher than on the busy one you have your task number 2. Normally, you should not pull. Otherwise, you are breaking the fairness of the scheduler.
I think the key point here is that load balancing is not based on the number of tasks in the run queue.
Yeah, this is like I said,
It's based on the load.
this picture is supposed to show the load, but I didn't know how to show that with boxes. So
No,
this
but-
isn't
but-
the number of guys in the queue. This is supposed to depict the
But
load.
how do you factor in your fitness score or whatever with the load? Because you could be looking at a very small task that would actually fit better on one of the other CPUs, or it could be a very big task.
True.
That I don't see being considered here
Yeah,
at all.
if we-
I mean, ignoring load and utilization is fine when you're talking about one task for each CPU or having gaps, I mean, idle CPUs in your system. But as soon as you have more than one task for each CPU, then you get into this mess that all tasks are not necessarily equal in terms of throughput
Right.
or compute demand. I mean, it's your duty cycle task that you were talking about yesterday in your Gini talk.
So first of all, let's be clear. What I'm trying to show here is load, not that there's two tasks. It's just that I don't know how to draw load. So the intent of this diagram and the intent of this scenario is when we've got a tie in load and we're going to pull from somebody, breaking the tie. Now, you're right. Once we say, gee, let's dive into that queue and pluck somebody out, was it a big pass or a tall cat? Now maybe we're on thin ice. Yeah, you're right. We could screw things up that way.
Yeah.
And all the things are you integrate this new input with the load balance to make sure that, I mean, that's probably doable, but
Move this.
yeah, sorry. I mean, the point is that how do you integrate this new input with the load balance to make sure that you will not break everything? I'm not saying it's not doable. It's just that you can't just blindly take this new index and forget everything else.
Yeah. Okay.
And you have to find a way to.
I think we're safe if we stick with a tie. I don't know how often a tie happens.
Len, is it the case that you use the load itself? I mean, only in the case when you figured out which is the busiest queue, having done that to pick which task to move is where you look at this fitness score. Is that the case, or do
Yeah.
you want to find the
Yes,
fitness score
so
even
the
to break
question
the
is,
tie?
the question is basically, are you considering the load first and the busyness and all that to make the decision to move? And only when you have a tie, are you using the classification?
That's our thought.
That's
We-
exactly right.
That's the original thought, yeah. So basically, we would add a tiebreaker, so we would be safe to not break what Vincent had pointed out. But if we delve in and pluck a random guy out of the middle of the queue, yeah, we could throw that off.
You guys, we're
Point taken.
out of time. Yeah.
Yeah, we have just a couple, I think one more scenario. And then we wanted to just mention EAS because it's in the title of the talk. And then there's this opportunity.
Yeah, in this case, is again a case in which we have equal loads in the wrong queues, and again, we are not ignoring the existing load calculations. We are using ITD to or classes of tasks to break ties between wrong queues and prefer one versus another one.
And here we could run into the same problem you just referred to, because if we pluck the wrong, if 1 and 2 are not the same size, yeah. So that's good. Thanks for pointing that out. And so we don't know how well this will. We didn't implemented this. We're like, hey, maybe this would be beneficial. I don't know. I don't know if this will be useful or extra complexity. But we should talk about EAS. And I think everybody in here probably knows how EAS works. Capacity model tied by tiebreakers with an energy model. And this is why we're not using it on Alder Lake. The first deal killer is that we have SMT, and you can't reliably calculate capacity when many times per second you're off by 50% or 200%. And even if we didn't have that on Intel chips, we've got a lot of opportunistic frequency range. So it's very difficult for us to track capacity when the capacity is opportunistic. Were those problems solved, then we've got challenges with the energy model. SMT impacts the energy model as well. Back in the beginning of the presentation, when I showed you that table that said this is the relative energy on this particular chip, that's a static energy model, which
Single point.
yeah, it's a static, which under some conditions might be true, but under many conditions is actually the opposite of reality. So on these particular parts, the E-cores are actually pretty high performance, and they can be driven to high frequencies and become relatively inefficient. They are indeed more efficient than P-cores from an energy point of view, but only when run at very low frequency. Under many conditions, as you saw, the IPC advantage of running on a P-core is rather large, sometimes enormous. And race to idle with something that races there twice as fast, where you can turn off a relatively inexpensive uncore, is actually a big win. So under many conditions, the P-cores are more efficient than running on the E-cores, which is counterintuitive. So that's a challenge we have with the energy model on this particular chip.
We're done. Sorry, you guys. It's like 5 minutes.
Oh, well, if there's,
We're done.
we have no more slides, but if there's any discussion on we get asked all the time, why aren't you running EAS on this chip? And so we want to be clear on that. I guess you all believed us.
Hi, everybody. I'm going to talk about something like that. Can even make it there. Yeah. I'm going to speak about something so that, oh yes, you're right. That's on something that have been discussed for, in fact, yeah, I have two parts in my presentation. So one is how to improve the latency of the CFS task. And the other part, which is probably the most controversial part, is how do you interface that with user space and how the user space can help to say which task should be scheduled first, I would say, or in priority. So let me start. So yeah, I'm going to. I can skip that. So I just want to remind to everybody what the CFS is about. It's about sharing CPU between a number of tasks and having a fair share of the CPU time. It's really about CPU time more than running first. And the goal is that the task with the lowest CPU runtime should run first. And that's what we are doing almost of the time. We have few, I would say, in order to be efficient, we can sometimes delay a bit this switch, but normally that's that. The lowest CPU runtime run first. Now, when we have several tasks with almost the same time, but different goal, so why should we not schedule the tasks which are latency sensitive first? Because this will not break the fairness between the tasks. That will just reorder instead of having a kind of a, if the VRun time is few microseconds lower, you will be scheduled first, but that doesn't make any real difference at the end from a scheduling period point of view. So that's really about that, reordering the task scheduling as long as we are quite close in the amount of time we have run so far. So yeah, the goal of my patch, I sent an update 4 or 5 days ago, is to add a latency int for the CFS entity. I mentioned I'm saying entity and not task because this can also be applied on C group and their scale entity. So the goal is really to add this kind of int and to try to schedule the entity with which is the most sensitive to the latency first, and to do that for each level of the schedule group. So either you don't want to preempt a task by something that don't really care to be scheduled fast. I mean, we have some background task. I will have an example where it doesn't care to be scheduled right now. You want this, I would say, sketch slice, but that can be in 10 milliseconds, that's fine. The opposite, we have other tasks that want to schedule first because it's part of a display pipeline, for example, but it's not an RT task. So we have to share the CPU, but why not giving in is 4 milliseconds, for example, in priority? And as I mentioned, because yes, that's something I really care about, is the goal is to not break the fairness and to not give an unlimited amount of time to some tasks just because they are latency sensitive. And usually that should make sense because usually when, if you are latency sensitive or if you are interactive, normally you should be short running tasks. You have to wake up regularly and to do something. That can happen sometimes that you need more time, but in this case, I would say the latency is no more a problem. You just need to get CPU. So this shows what is done at wake up right now. So the first one, just showing you what is happening. So when a task wake up, we compare its variant time with the current one. And unless you're 4 milliseconds for an 8 CPU back in the past, you will not preempt the task and you will wait the next tick. Okay? And what I'm proposing is to be able to move that in the range of the sched latency, which can be seen as the sched period where almost all the tasks should be scheduled. When you have a lot of tasks, it's extended because you can't bring the runtime of each task, but yes, usually that can be seen like that, as the virtual sched period. So the goal is to say, instead of not preempting unless you are more than 4 milliseconds in the past, for some tasks, which are latency, so low latency tolerant, so some tasks which are time sensitive, even if they are in the future compared to the current one, as long as you are in this sched period, you can still preempt it. You will use your sched slice, then go back to schedule either because you have finished or because it's the time for another one to run, and that's it. So at the end, normally you should not break the fairness, you will just reorder the way. And at the opposite, if you are tolerant to some high latency, you can say, okay, even if I'm in the past for several milliseconds, I can wait the next tick, and we will compare our preempt time at that time, and then I can run if it's the time for me to come up.
Question, yeah. So how are you handling the case where you have something that is like relatively CPU bound, but is like sleeping and waking up like constantly, but it's still doing work every time it wakes up. So it looks like you'll hit basically you're modifying the wake up preemption boost, but you're gonna get this preemption like all the time. Like, you know what I'm saying? Like, is that not a problem?
You mean between, sorry, can you repeat? I'm not sure.
Yeah, I'm just, so basically you're saying that something wakes up, right? And you're not supposed to preempt what was running, but you'll preempt it anyway, right? Because you have the hint.
Yeah, so the hint, yes, is used. So, or maybe it's in the, so what I have done is that, yes, I'm using a latency offset. And when I'm comparing the V-run time, if I have two tasks which are latency sensitive, so I'm taking into account the offset of both the current and the waking up, which means that if you try to preempt an already latency sensitive task, you can't, because you both want to run first, and you come back to the default behavior. That's the point. So, and if you're not able to preempt, that's what I have put later, is that, so I haven't gone in the detail, but I have a latency sensitive waiting list, which can be used so that if you can't preempt the current one, or if you're preempt because it's a RT task, for example, so you can't preempt the RT task. When it will be time for the CFS scheduler to select a task, it will check if there is a latency sensitive task that just wake up. It will put that first. It will redo this comparison of your runtime, and that's it. But as soon as you wake up, you are removed from this list, and you will be back to the normal. It's really for the wake up. And so that's so that just give you the kind of range at wake up. So yes, as I mentioned, it's really about comparing scaled entities. So the inside a C group, between C group, and then to root level, and so on. I don't know. I haven't. I have done that like that mainly because it's quite efficient, and you don't have to go through all the hierarchy, which can be painful at wake up. You want to wake up fast, but if you start to go through all the hierarchy, that can slow down everything. So, but we can probably consider doing propagating some kind of latency if needed. For now, I haven't seen any real use case of that.
So how do you propose to set that? I mean, you just set it for the final task, or you want to set it at every level?
I will mention that at the end, because that's probably the part that will raise most of the discussion, the interface. That's why. Here is what I want to do, and then it's how we communicate with the user space.
So what happens when everybody asks for this hint?
If everybody as a set is offset to the highest,
Yeah.
you're just compared like now. You're back to the, because what I have done in order to be quite easy is that I have the runtime, I'm adding this kind of latency offset on both the current and the waking up entity. So if both say I have a high latency, in fact, you will have,
My question isn't really that both, but do you have to search?
No.
Okay.
No, because it's only against the current. So the current, we already.
Current and the next.
Yes.
Okay, all right, thanks.
Are these entities typically the same weight, or do you think the latency sensitive ones are going to be weighted much more heavily? Because ideally you'd want to wake up the low latency ones, or the ones that are not latency sensitive on CPUs already running other non-latency sensitive tasks, rather than target them to wake up against latency sensitive tasks.
So right now, I'm only happening when we check if we can preempt the current one. I haven't done anything typically when we are selecting a CPU in the select idle sibling or the wake affine. I haven't done anything yet there. Maybe that we can do some kind of improvement, especially when we are comparing the previous and the target. If there is an obvious choice to do, yes, that can probably be done. But I haven't done that yet. Yeah.
Trying to go back to Joel's question, what if you have like two tasks that are both like same priority level, so same nice level, and they are also busy loops, let's say, but one is doing like a micro sleep every 5 milliseconds. Is not that the corner case where you end up using the CPU only for that task?
So when you say same nice priority or latency nice priority?
Same nice priority. So you should give like 50% CPU to both tasks, but one is the OG and it just does like 1 microsecond sleep every 5 milliseconds.
So if one, it's all about the VRAM time.
Yeah, exactly. But we end up always refreshing the VRAM time for that task just because it goes to sleep. I mean, if it goes to sleep because of I/O, it's one reason. If you go to sleep because of a micro sleep from user space, then probably you can abuse the.
Right now, I don't make any difference between an I/O sleep and a normal sleep.
Yeah.
That's
where I think the task that does the sleep, it can take more CPU and break the fairness.
No, but you can't because it's only at wake up. But at the end, let's say that, for example, you have, if one task start to wake up every, I would say, wake up every millisecond and run 999 microseconds, at the end, your runtime will continue to increase and you will go outside this range of the skate period. So you will not be able to preempt anymore the other one.
But we have normalization of the runtime when you wake up. No?
Then you're kind of back to where you started, right? Because you have latencies again, no?
Sorry?
So yeah, so the runtime moves forward.
Yeah.
And now you're outside the window.
Yeah.
So the next time you wake up, this won't happen. So isn't that like you're back to where you started?
Yes.
Right.
Yeah, because it also means that you have used more already all your running time budget. That's the point.
It's like a temporary boost.
That the point is just that as long as you're not trying to use more than your runtime budget, you will run first. If you start, and that's really what I don't want. Otherwise, yes, that's a way to, you wake up, you just do a 1 microsecond sleep and you will get a full budget. No, it's not possible.
Essentially a rate limiter, right?
Yeah.
I mean, the other thing which I guess you're not doing is trying to make a decision on where to wake up. This is just on wake up, do you preempt?
Yeah, no, right now it's only at the end when you have, after selecting a CPU, should I preempt the current running task or not? As I mentioned, I haven't looked. Maybe we can do some obvious choice earlier, but I haven't looked at that yet.
Okay.
Because we start to be, should we select an idle CPU or not? That start to be raise more discussion, to be honest.
Right. I mean, it's not just the idle CPU, right? Can we take the least busy CPU in variable load?
When you mean around the non-idle CPU or around idle CPU?
Around non-idle CPUs.
Around non-idle, yes, probably at wake, I think we can probably look at the priority of the current between previous and next and target, and take the one with the lowest one to get more chance to preempt. That should be doable. It's quite straightforward. It's just one, I would say, one comparison. That should be doable, yes.
Vincent, in a corner case where you have the current task that is running at nice minus 19, but it has not set latency nice, and you have the waking task which is probably at nice 19, but it has a latency nice of minus 19.
Yeah.
It's more latency. So in that case, it would preempt the current task because it is more latency sensitive, but it probably would not run for long enough, right?
Yes.
That's
yeah, but that's I agree. Yes, if you can run, let's say, 1 millisecond every second because of your nice priority, if you want to run more than 1 millisecond, you will be you will screw up.
So latency lies only about how quickly can you get on the run queue, not how long can you run on the run.
No,
That's
no.
still nice.
Yes,
right?
yes. Just reordering at wake up. So yeah, so maybe I haven't mentioned that much, but it's a signed value, so you can ask to preempt in advance the current task when you're latency sensitive, but at the opposite, you can say that I don't care. Just let me be scheduled at the next tick. And if you look at that bench, which is a use case where we have this kind of problem where we have a lot of tasks that waking up all the time, preempting each other. And in fact, the task doesn't make any progress before being preempted. And that's especially true in the process mode. And I think it's probably because you have to switch the context between each thread and so on. So I have run the AG bench with two nice latencies. So the first one is this one, the default value. And here I just put that to latency nice 19, saying that just wait, I don't mind. And you see the benefit just because you're minimizing the number of preemption and context switch, and that's it. So if you know that your tasks don't really care about being scheduled fast, that will just improve. You will, from a statistic point of view, there is more chance that you will have a full slice because you will have wait really at the end of the schedule period, and you will not be preempted unless there is a latency sensitive one. Okay, I will try to. So here then it's, I have done try to characterize on the opposite side. So what I have done is that I'm running a cyclic test with a nice latency nice priority, minus 20 in this case. So which means I'm really sensitive in the CFS scheduling class. And at the same time, I'm scheduling AG bench with a lot of thread, which create a lot of noise and a lot of wake-up preemption condition with the default priority. So in this case, AG bench has the default, the normal wake-up behavior. So you can see there for latency 0 for the cyclic test and latency minus 20. So so this is the patch set without the last patch of the patch set. So we can still see that the max latency is almost the same. I mean, I have 58 and 82 milliseconds in one side or the other one, but that really changed. The max value can vary a lot. Just because without the last patch, there was some corner case where you can be preempted by RT and so on. And then in this case, you're back in the normal way of working, and you have to wait your turn. But nevertheless, you can see that if you go up to the 99 percentile, so you're still quite low, which means that almost all the cases you have been able to preempt in advance. Whereas with the normal, you are above. So yes, my histogram was up to 20 milliseconds. So that's why the 99 percentile is above 20 milliseconds. On the other side there, So I have just added this additional arbitrary for the waking latency sensitive tasks. So it's only tasks which have a negative latency sensitive value. And this have been able to cover this kind of corner case there. It's just because that if you wake up in advance and you're preempted by an RT task or whatever, or a stop class, you will be put in this waiting list because we consider you haven't been able to run your slice at wake up. So you will have another chance to run first. That was able to cover the, so we see that, yeah, the difference up to 95% is quite similar. That's really cut the end of the tail of the long latency. And so I haven't seen any major difference if you use the default latency nice value. There is almost no difference because it's probably, I think I can't remember exactly, but that's probably something like the read of a field in the scale entity and a comparison. So that's almost nothing compared to the other things that we are doing. So that was for the implementation, and then the interface. So the goal of the interface is to let user define a priority, or being able to prioritize the task between each other. So the goal is to have a signed value because you can say I'm latency sensitive, or the opposite, I'm not at all. There were several attempts to find a generic interface. The one that I took was done by Pratt there. And the goal was to use a latency nice priority, to be quite similar to the nice priority. Because, it's already the case when you're setting a nice priority that you don't really know how much CPU bandwidth you will have, because you don't know who else is running on the CPU. So the goal was to be the same, to give a kind of a relative priority instead of more than an absolute priority. So that's what I'm using for the task, for setting the priority of a task.
So
on the C group side, yes.
Can you just expand a bit more on the latency nice priority? I mean, what does it translate into the absolute offsets?
I have a table, so I have an offset which range between minus scaled latency up to scaled latency. Minus 20 is minus scaled latency, and the latency priority 19 is the
factor of 2 every time.
So it's a linear of things.
Oh,
I have
linear.
it's linear.
And I guess a bit that I had problems earlier when we were doing this. It did not translate well across different CPUs, right? Does it translate well here?
Not more, because it's not at all that. It's not related at all to which kind of CPU you are running on. It's really about on the wake up, preempt check wake up in the scheduler, and that's it. So
you can continue. I can ask later.
Sorry?
We can talk later if you want to finish. So I was going to ask you just about the interface, right? So we have a real problem with latency of tasks within C groups. Because if you have C group with tasks that are latency bound and IO bound, for example, then at the root level, the whole C group can look like it is CPU bound, in terms of its vRun time, right? Because you compare the vRun time on top. So I was kind of thinking like this sort of hinting is good, but for this problem, I feel like the hinting should be sort of automatic because you have a task inside the C group that's supposed to be like low latency, right? Because CFS gives tasks that sleep a lot. It gives it dynamic priority boost already, right? And it should be allowed to run. So how would you solve that, right? Because the vRun time is combined for the entire C group. So I was thinking like if for this problem, because you're hinting at the sched entity level, if you can make the hinting automatic somehow and give that C group lower latency than, you know what I'm saying? Like, so
Yeah,
that the task inside the C group that has been sleeping a lot will actually get a chance to run.
So yeah, for now, yeah, that's in the C group. I have added a CPU latency interface, on which you can directly set this offset between the scale latency in the scale latency range. So there was some discussion. Tejun was a bit concerned about having a nice value. He would prefer an absolute value, so that's what I have put. To be honest, I don't know if people who will use this can really make a sense of the value they will put. For example, minus 20 milliseconds, what does it mean at the end? Compared to minus 20.
Yeah.
But yeah, I don't have any strong opinion. Maybe I'm too focused on the internal to know exactly what will be really useful.
Are you sure you need more than 1 bit?
Yes, I think so, because you can classify, that help you to classify between, I mean, saying I'm latency sensitive, if you start to have only a true or false, everybody want to be latency.
Well, everybody's going to ask for minus 20 anyway. Isn't that the same
Maybe.
as setting the bit?
Yeah, but we can, and with the C group, we can I can easily imagine the system manager to classify that a bit, just like RT.
That's
I mean,
fair.
we-
The
yeah.
system manager could do it. Okay.
With RT, we have the same. If you ask, everybody want to have the highest RT priority, but the system manager just have a better knowledge and can just order the things. For me, that's quite similar. But that's, yeah, I don't have any, I think this is working well, and this have been, yeah, that was the last slide. These have been discussed quite a while, so that's why I just wanted to reuse all the discussion that have been done by Prad, by Joel, maybe also Patrick. So there was a kind of consensus on this interface. Yeah. Okay. Take a mic for the online people.
What do you do when you have a CFS task in a group, right? And you apply this value to the group, and the task has its own value. Is it somehow aggregated, or do you take the group value?
No, right now it's really per levels. I mean, if you set latency nice of a task, that will be done inside the group. And then the group, if you want the group to be scheduled before others, you will have to set the latency of the group.
Okay.
So it will be scheduled
It's
first.
about the shared entity for the group.
Yeah.
Okay,
yeah.
cool. And last thing, we started this whole latency nice thing for the workloads where we check the CPU we're going to put stuff on, or we wanted to consolidate CPUs. I think this was past use case. But we said immediately that it's hard to define latency nice for those use cases, and that's why I think you came up with something more sane.
Yeah.
That's why, because when we have now also people saying that maybe it's nice to find the next CPU, which this is something we started off from.
So yeah,
Okay.
We are back to something which become more and more platform specific, because some people on that I haven't any real answer.
Okay.
Thank you.
Yeah, think we are back.
Hello? Yep.
Yeah. So
Vai fora e virar o que se pode mexer. Hello, good afternoon. It's time to get back to the real-time scheduling micro conference, and we invite everybody to follow the presentation. We call
Screen. The other one. The three dots on the slides.
That's what I did.
No, the one below. Exit this, escape. Yeah. No.
Okay.
You see the three dots? Not there. Three dots on the slides.
Ah, okay. All right. Thanks. All right. Welcome back. My name is Gautam Shenoy. I work for AMD, and this is a work that I've done along with Pratik Naik, a new college graduate who joined us recently. And we want to discuss some of the scheduling challenges on split LLC architectures that we've been observing in the last few months. There were more problems, but thanks to the efforts of the community, we have been able to make progress. Thanks to Mel, we've seen the NUMA imbalance issue being fixed, but there are still a lot more challenges out there which we would like to discuss and see what are the options that we have to address them. So to give you a quick context, by split LLC and unified LLC, I mean that by unified LLC, I mean the last level cache being at the level of a socket. So if you see the SCED domain hierarchy for these kinds of processes, it's going to be the SMT domain, then you have the MC domain, which models the LLC, and then if it's a multi-socket system, you have a NUMA domain. Whereas for a split LLC, you will have SMT, MC, which is the group of cores which share the last level cache, L3 cache. And then you have the die, which basically has multiple such MC domains, multiple such LLCs. And then you have the NUMA. So that's the difference if you want to compare it side by side. I should have had a slide, but I'm just showing you with the diagram here. So some of the challenges are classic challenges with respect to the problem of consolidation versus spread, right? I mean, there are certain classes of workloads that like to be consolidated, and there are certain classes of workloads that like to spread. So I just want to talk about three such problems and why we are not able to make the right decision currently, and what is it that we can do to sort of address this problem. So for the problem of wanting to consolidate but not being able to, we use the example of SCH bench. SCH bench has, in this variant, we have a messenger thread and a bunch of worker threads. And the messenger basically wakes up the workers, and workers are done, they wake up the messenger, and what we measure is the tail latency. And what we've seen is we get the best tail latency when the messengers and the workers are in the same last level cache. They are running in the same LLC. And when that does not happen, you see a very bad latency. So in a good case to bad case, we've seen like 2 point, I mean, if it's 1 normalized in good case, it is as bad as 2.5 in the bad case. And it's not that the scheduler today does not make use of any hints to sort of try to bias the wakey towards the waker in the wake up path. We use the WF sync flag, and when that happens, and when we know that the run queue length is only 1, which means that the waker is going to go away, we try to wake up the wakey on the same LLC. So that's the hint where we already use. But in the case of SCH bench, it uses Futex to signal the workers and the messengers. And WF sync flag does not feature here. So what happens is when you initially create this workload, you have, because of the way we do initial placement, you'll have the messengers and workers being spread across all the different LLCs. And then we would like them to consolidate, but because we don't have any appropriate signal, they'll continue to be woken up wherever they last ran, right? But consolidation does happen. It's not because of a conscious choice, but it is because of a noise. So what we observed was the reason for this run-to-run variance is really how quickly the consolidation happens. If the consolidation happens earlier, your tail latency is less, as opposed to when it happens much later on. And the reason why we observed, when we analyzed, why is the consolidation not happening in a deterministic manner, the consolidation is happening in the new idle load balancer case, especially when you have a K worker or some kernel thread pop up, and that has to be a per CPU kernel thread because it cannot be migrated. It pops up on one of the CPUs where the SCH bench worker is currently running. And at the same time, the messenger goes idle. And in the new idle load balancer case, it detects that, hey, there is an imbalance here. I have 0 tasks locally, but there are 2 tasks out there. I cannot move the pinned K worker or the kernel thread, so let me move the SCH bench worker. So that's how the migration happens. But really, we are at the mercy of this noise, to help us do the consolidation. And there is enough noise. It's not that it's not there. It's just that it's not deterministic. And it's not, we are doing this consolidation consciously. So this is one problem where, in the absence of any specific heuristics that tell the scheduler that these two are communicating tasks, we do not end up communicating, thereby hurting the performance. And in case where the consolidation does happen, since it does not happen deterministically, we see a run-to-run variance, which is also not the ideal case. So this is the problem where consolidation is preferred, but we do not get it. The next problem is with respect to the case where we would ideally like the workload to be spread out because the workload is a bandwidth constrained workload. So the example that we've chosen here is that of the stream workload. So consider the case where we have 2-socket third generation EPIC system where this test was carried out. It has 8 LLCs per socket. So in total you have 16 LLCs. So if I start a stream application with 16 stream Mel's latest enhancements, we are in most cases able to spread it out and make sure that each LLC has only one stream task, because that's ideally what we want. We don't want more than one stream task on the same LLC. They'll be thrashing each other's cache, and that's not an ideal situation. However, consider the case that we have placed the first 15 stream tasks on each of the LLCs, and there was, in the diagram there you can see there is a LLC that has a blue colored thing. Some oddball task was running at that point in time. So what we do in the initial placement is we compare the number of idle CPUs in the two domains when we are trying to compare and find out which is the idlest domain. And since the number of idle CPUs are the same, what we do is we end up waking it up on the LLC of the parent, where the parent is currently running. And in such a case, you will have 2 stream threads on the same LLC, which is LLC 0. And that blue thing can go away. It's probably going to go away. It's just a noise, but that's going to go away. But because of the way we have these NUMA imbalance thresholds, because the difference is 9 and 7, which is less than or equal to 2, it will never equalize, right? So throughout this run, this is what the situation is going to remain. And hence, in this case, we'll see a very bad throughput. And this is responsible for the run-to-run variance. Now, previously, we were not seeing this because before Mel made these changes, it was bad in all cases. We would end up consolidating all of these onto a single NUMA node. It would not even go to the other NUMA node, and it was uniformly bad. But after Mel's changes, we started seeing very, very good numbers in the good cases, but there are these oddball cases where we do see bad numbers. So based on the heuristics that we have currently, and then we try to see if some other signals can be used to break the tie. We tried using something like group utilization, which is the utilization of all the cores in the group, to see if we can break the tie and then move the task towards the one which has a lower utilization. Now, this was good for stream in most cases, not all cases, but it was causing regressions on other benchmarks which preferred consolidation, like Hackbench was not happy with this. So this was another issue where spread was preferred, but we could not spread early enough or consistently enough, and that caused regression when it was not expected. And the final example that I have here, I'm using T-Bench, where basically we have this thundering herd sort of a problem on a 2-socket system that we can observe. So basically, T-Bench, you can spawn n number of clients, and then you have the T-Bench server, which basically pairs each client with each server thread. So you have pairs of clients and servers they're communicating via TCP, right? So ideally, you just like these client and servers to be co-located. I mean, but it's all right if you can spread them out, as long as the client and servers are co-located. However, this has an interesting property that when the client sort of is initially placed, it goes immediately to sleep. It waits for all the clients to come up. So you've placed it on LLC 0, right? Because that was the idlest LLC probably. It goes to sleep. So the number of, you have enough number of idle CPUs there. So that when the next client wakes, initially it has to be placed, it'll again be very likely placed on the same LLC. It goes to sleep. And that happens consistently until all the clients have been started. And then all of a sudden, everybody wakes up. They're all there. And then you have to rely on the load balancer to sort of, move them efficiently across. And when you have, this is what the initial distribution looks like. So you can see that in the table there, a lot of the tasks were on LLC 14 and 15 initially, right? That's what the distribution was like. And it was all on one NUMA node consisting of LLCs 8 to 15. And the distribution was something like 17% and 82% initial task placement. And we counted that we need something like 10,000 migrations before we could get to a semblance of equality. We cannot get perfect equality, but to get there, right? And in case, if there's a way by which we could get the initial placement right, in this case, we saw that we could observe something like 20% improvement when we had 64 clients, 12% improvement in the 128 clients, and this is consistently being observable. So when we are initially placing the task, scheduler has no history of what the task is, and it tries to do the best it can, right? And in this case, because of the nature of the workload, it tries to beat that. Because it goes to sleep and then wakes up eventually when all the tasks are there. So you have this thundering herd problem, which the scheduler could not have predicted. So try as hard as we do today, we are not able to completely get what the workload really wants. And we do use the heuristics as best as we can, but that's still not sufficient. So another interesting thing that we observed is, one of the differences between a unified LLC and a split LLC is that because the L3 cache is at the socket domain, since if you have AutoNuma running, if there are a pair of tasks that are spread across two NUMA domains that communicate with each other, very likely they are going to be using the same set of pages. So AutoNuma would pull them together, right? And as a result, they get the side effect of using the unified LLC out there, but unified cache out there. Whereas on split LLC, AutoNuma at best can co-locate them onto the same node, but it does not guarantee that they'll be in the same LLC domain. So that's where AutoNuma's effect ends. So that's another sort of shortcoming. And of course, there is another advantage that when you have a task that is waking up, in the wake up logic, we use the MC domain to figure out if there is an idle core or an idle CPU. In the unified LLC domain, you have a higher probability because there are a lot more CPUs there. You have a higher probability of finding an idle CPU, though it comes with its own set of problems. I think Chenyu is going to talk about that in the next talk. But in split LLC, you are limited. The search space is limited. So if you don't have an idle core out there, you're just going to pile on behind onto one of the busy run queues, and then you have to hope for the load balancer to move you around. So these are some of the observations that we had, that we would, there is no way currently that the scheduler can detect, whether it prefers spread or whether the workload prefers consolidation. And the negative impact is particularly high when you have this split LLC, because then you end up paying a penalty when you get the displacement decision incorrect. So what have we tried out? Well, sometime after last LPC, Peter mentioned that, I think it was one of the threads where we're trying to optimize wake wide, that we are not sure whether adding more heuristics is going to improve the situation, because a heuristic may favor one class of workloads, but it's definitely going to be biasing against another class of workloads. So is it possible, that we can look at some hints from the user space? Latency nice is what Vincent spoke about in terms of latency, and Peter enumerated a bunch of hints out there, whether it's energy efficient, background, and so on and so forth. So can we use this mechanism of hinting from the user space to help the scheduler make better decisions? Especially if the workload knows what is it that it wants. if we do get a hint, it's not necessary that the scheduler has to honor the hint all the time, but in case where it is possible, right, can we make better placement decisions in case we get some hints from the user? So what we explored was a very simple model out here. This is not meant for inclusion. We've sent out the RFC patches. This is just to spark some discussion here. During the initial placement, you could, because the scheduler has no history of what the task has been doing, if we get a hint saying that, hey, this is what we prefer to be spread away from the parent, or we prefer to be consolidated close to the parent. And similarly, during the subsequent wake up, do you want to be woken up closer to the waker, or do you want to remain where you previously ran? So if we get some hints like this, does it help the workload? So we enumerated all possible combinations for these workloads. There's some of that we've been investigating, and we do see that hints are useful. For instance, for SCH bench, in most cases, except the overloaded case, we do see that when you provide the hint to affine during the fork time, that is, you wake up the messengers and the workers close together on the same LLC, you do see consistently that the tail latency is better. So even in the cases where, in this case, we have 16 CPUs per LLC. So even in the case where you have 32 workers, 64 workers, it is preferable to start them on the same LLC and then let the load balancer sort of spread them out, rather than start them far away and then hope that the load balancer or the wake up path consolidate. So this kind of a hint was found to be useful. And then if you give an incorrect hint, like in case you gave a hint that asked it to spread for whatever reason, you do see the negative impact. So that's the problem with hints. Like, you are really assuming that the user knows what they want, and if they want to shoot themselves in the foot, that's what. Yeah.
So just where do these hints help more, right? I mean, in a system that's more loaded, in a system that's less loaded, on a heavily loaded system, would something like fork affine be more useful than a less loaded system?
So on a more heavily loaded system, for SCH bench, fork affine is not useful. We can see that in the 256 case where pushing everything, consolidate everything to the single LLC was bad, right? So we are really assuming at this point in time that the workload, when it's asking for a hint, it really knows what it's asking for. So whereas, something like where it can say that, hey, I am a heavily loaded system, and in case you can explore beyond an LLC domain when you want to wake up a task, that allows you to spread faster, right? SD wake balance, which we used to have at one point in time, that may help in the heavily loaded systems, if that's the hint that you want to provide. But like I said, the implementation makes sure that if there are no idle cores during the wake up or during the initial task placement, in the choice that we have, we ignore the hints. We don't take the hints, and we fall back to what the scheduler is currently doing. This is only beneficial when it is possible for you to find an idle core. That's what we use as a cutoff point to decide, hey, when do we ignore the hints? And similarly for Hackbench and Tbench, we see that for Hackbench, affining both during the initial placement as well as during the subsequent wake up was helpful, and spreading it out was not so helpful. Whereas for Tbench, spreading it out during the initial placement was much more beneficial, especially for the higher thread counts there, higher worker counts. Sorry.
So another question, right? What is the ideal distribution? Can you think about the ideal distribution and maybe pin stuff and give us a difference?
Can you repeat that?
What is the ideal distribution?
The ideal solution would be for the scheduler to know.
No, not the ideal solution. Ideal distribution, right? If you could, knowing the information like this is what's going to happen. Say this is where you must wake up. This is where you must be placed initially, which you could probably do by pinning and run an experiment to know.
Right. So for instance, let's take the SH bench case. If you chose the case where you said, hey, I'm going to pin everything together in the 256 case, especially in the cases where you have high utilization. When we pinned, we saw that when the number of clients were greater than the number of CPUs available, the tail latencies were terrible. So you could pin in certain situations where you have more number of CPUs than you have the number of tasks.
But again, that's something that you have to do for each task that the workload provides. Whereas here, the way we have implemented is you provide the hint using PRCTL, and when you subsequently fork, the children inherit the hint provided by the parent. So in terms of consumability, that gets passed down. And we are assuming that the children would like to have the same kind of hint that the parent has, unless they choose to change it. Yeah, so we wanted to present this to see, what would be the right approach going forward. Something like user space hints useful? Can we, explore a wider range of tasks, wider range of workloads? Because given the situation that we have, I mean, the current heuristics are simply not working, and I don't know whether we would want to add any more heuristics.
I think we are, out of time. Yeah, thank you.
Okay, thank you.
So next presenters, I think, are online. So if they can maybe activate also their webcam, I think we can see them on the screen. Yeah, can we raise the remote mic? It's on, okay. Yeah, can you guys say something so that we can check if we can hear you?
Hi everyone.
Yep. Yes, works. Yeah, so go ahead when you want.
Do you guys know how to change the presentation?
It's the press the right corner to switch the slide.
Yeah, he's the presenter.
Okay, and then he knows how. Oh, wait, was he needed? Yeah. So why do you need it? Or why yeah. No, you don't want it. He's got the presenter, right?
Yeah. You
Okay,
change. Okay,
yeah.
that's it.
Okay.
Go ahead.
Okay. Hi everyone. My name is Chen Yu, and I'm from Intel. I have been working on the task wake up optimization for the past few months. And last year's LPC conference, there was a discussion on improving the idle scan efficiency. Today we are going to give some following up updates in this area. I would like to seek suggestion on the next step. So here is a brief introduction of the problems. The first problem is the scan wastes too much time searching for an idle CPU, especially when the system is overloaded. To mitigate this symptom, two approaches are proposed. The first one is the sysutil, which limits the scan depth based on the system average utilization. And it has been merged recently, so I will not talk about this in detail, but besides, there is an ongoing effort to leverage the CPU, idle CPU mask to speed up the search, which is currently called sysfilter. The second problem is what we encountered recently. We found the cross CPU wake up issue when running some workloads with frequent context switch. I will talk about this cross CPU wake up issue in detail, and Abel will talk about the sysfilter later. So although the sysutil can improve scan efficiency, it cannot deal with the cross-CPU wake-up issue. We use real-scale benchmark to reproduce this issue. One subtest of real-scale will leverage the pipe read and pipe write to strengthen the scheduler. According to the result of the top command, which is marked as red, when this issue happens, the idle percentage is around 30%, even if the system is saturated by many tasks. The reason why we think the idle percentage is abnormal is that if we set the CPU affinity for these workloads to stop them from migrating among CPUs, the idle percentage dropped to nearly 0%, and the throughput increased by about 300%. According to the PERP profiling backtrace, the bottleneck is the run queue spin lock. It shows that the system wastes a lot of time spinning on the run queue lock. And shown by the PERP profile, task A is the first backtrace wants to wake up task B on CPU 1. Then task A grabs the run queue lock of CPU 1. If CPU 1 is about to quit idle, which is shown in the second backtrace, it needs to grab its own lock, but it has been taken by someone else. Then the idle task takes more time to quit, and the waste of time on run queue lock hurts the performance. During the recent 6.0 merge window, the wake list mechanism has been enhanced. If the wake key CPU is idle, then use the wake list to offload the CPU activation to the idle CPU. This is actually done by sending IPI or setting the pulling flag to kick the idle CPU. The benefit is that the cross run queue lock contention has disappeared. However, we still observe around 30% of idle duration. According to the second perf backtrace, the idle task spent quite some time on skilled TTW pending, which is marked in the. This function is the core logic to enqueue the wake key when idle quits. But the side effect is that it would take more time for the idle task to quit. Here is a possible scenario to explain this problem. Since skilled TTW pending delayed the quit of idle, in step 2, the idle duration looks longer. Then in step 3, this non-idle duration would mislead sysutil. Later, sysutil suggests the waker scan for more CPUs. The time spent on searching for an idle CPU would make wake key waiting for more time, which in turn leads to more idle time. So this looks like a chain reaction, and the symptom has raised a question. If the system is busy, and if the wake workloads are doing frequent context switch, is it still a good idea to spread the wake key on different CPUs? So in last year's LPC and also in Vincent's presentation, and Vincent and Rick proposed a direction. Can we consider the task running time during the wake up? So in our test case, the task is doing context switch frequently. It is regarded as a short running task. Then we propose an experimental patch in this direction to check if it helps. The idea is that if the system is busy, and if the waker and the wake key are both short running tasks, the wake key could be put on the waker CPU safely. The reason is that if the waker is a short running task, it might relinquish the CPU soon, and the wake key has a chance to be scheduled. On the other hand, if the wake key is also a short running task, the impact it brings to the target CPU is small. So if the system is already busy, maybe we could lower the bar to find an idle CPU. The effect of this change is that the wake affinity is enhanced and the cross-run queue wake up is reduced. By now, we launched some micro benchmarks using kernel 6.0 RC4. According to the test result, with the patch applied, netperf, hackbench, and wheel scale benefit more less. And there's no noticeable difference in T-bench. The figure on the left is the netperf result. The y-axis is a improvement percent. The x-axis is the number of netperf threads. So we found when the system gets saturated, the throughput increases by more than 100%. The reason why we did not see any improvement when the system is extremely busy might be that the sysutil has already taken care of the overloaded scenario. So this benefit might come from two parts. One is the reducing of the cross CPU wake up, and another is the cache liquidity. The figure on the right is the hackbench. We notice some improvement when the system is saturated, and this result is aligned with wheel scale. The pipe workloads benefit most. By now, the experiment patch only has test data on throughput. We are also thinking of run other benchmark to see if there's any impact to tail latency. But before that, I'm not sure if it is a great way to solve this cross-run queue wake-up issue by enhancing the wake affinity. And it would be appreciated for any feedback on this. Yeah.
Okay. Can you hear me?
Yeah.
Yes.
Yes.
Hi, Chen. Did you finish?
Where should I give you the presenter?
Okay.
Hey, sorry, I had a question for the current presentation. One thing you said is if the the waker is a short running, you wanted to wake up the wakey in the same CPU, if I'm not mistaken.
Yeah.
And I'm not opposed to that, but I feel like this is more of a generic issue that's not related to really how long the waker is running. It's more like how long between the time you wake up to when the waker goes back to sleep. That seems like a more of a generic problem that would be better to solve it in a more generic way than just focusing it on short running tasks. Put another
I
way,
think
we see the same issue on Android too, where a long running thread will wake up another thread and it's going to go to sleep in another few microseconds. Where it would have been better to run the key on the same CPU, but it ends up getting scheduled elsewhere. So maybe like a generic solution for that would be better than focusing on the runtime of the waker.
The issue is more severe because when the task is a short running task, because that indicate a more frequent context switch, and context switch will cause the task wake. Right, the problem will be more severe when there are more frequent context switch. But if the task is a non-running task, the cross CPU wake up might be less number of that. Right. That's my thought. Yeah. But yeah, we can still consider. So besides the short running task, I think Vincent has also proposed that we can consider the long task. For a non-running task, we should try our best to put it on a completed idle CPU or core, because it might indicate that it requires more resource or something like that. Yeah.
One quick point to kind of set some context. When I say long running, I'm talking 10 milliseconds is long running.
Okay.
Just to make sure we're on the same page.
We can move on. Thank you.
Yeah, okay.
Should I make Abel the presenter?
Yeah, I think so.
Okay.
So 10 minutes warning.
Yeah, and 10 minutes warning.
Okay, hi everyone. Good afternoon. My name is Wu Yun and I'm working for ByteDance, the parent company of TikTok. Today I will talk about my recent work on improving SRS scan efficiency. Okay. The three-step agenda, the background, why we need the feature, and the filter how it works, and benchmark how much benefit it brings. Okay, let's first check the background. SRS is the fast path of selecting and run queue to place the CFS task. It plays an important role in maximizing the utilization of CPU resources. When selecting, cache-hot CPUs are given the most preference, and if they are busy, then a domain scan on target LC is fine, trying to locate an idle core or idle CPUs. And the SIS domain scan is the part where the filter targets at. Okay, currently, it scans in a linear fashion through the LLC domain. So the worst case cost is well bounded in small LLCs. The PC, the figure below. If the LLC only has 4 CPUs, then the worst case cost is peaking at the 4 CPUs, nothing more. It is acceptable, although it would be better if there are some magic to tell us try the last CPU first, but no free lunch, right? Okay, as the LLCs become bigger, the linear scanner also plays well under light pressure. See the first part of the second LLC. But once the load increases, more CPUs need to be scanned, so the scalability is questioned. And the schedule features SIS prop was born to limit the scan depth. Recently, a nice work done by chain called SRSUtil has been merged into the mainline kernel to replace the SI prop, and it makes the scan depth proportional to the load of the target LLC, which sounds more reasonable. Okay, with the limited scan, the cost of domain scan is well bounded, even in large LLCs. Yet it would still be better if more widely scanned can be. And this is what the SS filter born for, together with SIS util to better fit the trends in the real world. Okay, nowadays, lots of cloud service providers are trying to reduce TCO of their data centers by co-locating multiple workloads together to squeeze all kinds of resources. And in the meantime, the LCs are also getting bigger than before. With the filter, the busy CPUs are skipped, so the idle ones can be easily located, as the figure below shows. Although there might be some false positives that we will talk about later, it makes the scan much more efficient. Okay, let's check how the filter works. The filter is a CPU mask resident in the LLC shared schedule domain. It is supposed to contain idle or schedule idle CPUs along with some false positive CPUs. The CPUs are set into the filter when they become idle at core grain. Please see the figure below. The number indicates core numbers, and the alphabet shows the SMT siblings. When CPU 2A, which is the first CPU of core 2, goes idle, it will be set in the filter. Because 2B is not set, so 2A, when 2A goes to idle, it is set to the filter. But if you take CPU 3A, for example, 3A is already set in the filter, so the propagation can be skipped, and then we don't need to do the update. Well, the tricky part is the 4A in the picture. The propagation will also be skipped if its sibling is present in the filter. So this is why it's called co-granular updating. It can reduce the LLC cache traffic. Yeah, don't forget it is LLC shared CPU mask, and can also bring benefit by avoid stacking the task on single core, which makes the load more balanced. While the downside of co-granular updating is that some idle CPUs can be missed due to their siblings are present. Well, it seems not a problem if the false positives can be corrected properly. Okay, and Jury, do you have any questions? Okay, let's.
Yeah, we have
Okay,
5
let's
minutes.
continue.
Yeah,
Oh,
a
please,
second.
please.
Hi. So there was a talk yesterday by Julia Laval on the Nest scheduling changes. It's the research paper she's written, where she talks about something similar to this, where they are building this nest of CPUs which are constantly reused. And so she showed an interesting graph where, in the wake-up path, when you're doing the scanning, the wake-up path tends to pick CPUs linearly, like one after the other. And so you end up waking up cold CPUs instead of like hot ones, possibly with cold L1 caches and stuff like that. So I was wondering if, one of the things I was thinking was personally to explore whether some of the changes she has made, can be used to fix the wake-up path and do a better job than just like constantly spreading tasks on the wake-up path. And it sounds like this is a similar problem, but it's not the same thing. But I just wanted to bring it up. Do you see any?
Yeah, I see. Jury had worked on this in 2020. If I remember correctly.
Yeah, I think so. So basically, my point is that because she's constraining the number of CPUs, it sounds like that will itself reduce the amount of scanning, right? Like because you're building this nest of CPUs instead of having a search space, the entire like LLC or whatever. You're restricting it, which will also improve the scanning speed, right?
Yes, yes, it is.
So I feel like the problems overlap, and yeah, do you think so as well? Yeah. Yeah, so something to think about.
Mel?
I think the two ideas of the nested versus idle search are related, but not necessarily the same thing. Because when searching within a nested CPU, you're looking for a CPU that is idle, but recently idle, whereas this presentation is more about finding idle CPUs of any type, but would be related. If there was like a nesting mask, it would make sense to try and find an idle CPU within the nest first, and then if one is not available, which is perfectly possible, use the idle mask in this presentation to find an idle CPU regardless of coldness state, like whether it's in a deep sea state or cache cold or whatever else. So I think the ideas can complement each other. I don't think they contradict each other.
Okay.
1 minute.
Okay, please.
I'm just wondering whether it's been considered to organize this as a tree. So basically, I think it's kind of the weight. So each CPU has a usage, and then based on its idleness, I mean, some might be less used than others. So if they are organized by ordered within the tree, and then you get, let's say, the most idle CPU at the bottom of the tree, then you could even use do nearby lookups to do, oh, okay, what is the nearest to me that is idle, or what is the most idle in the system, and that should limit the scan to something quite limited.
A tree would be expensive to maintain, but the idea still has merit because the CPU mask could be done in multiple passes. So the first pass would be within the nest, the second pass would be in idle CPU, and the third pass would be the entire domain, with the search depth limited by whatever sysutil tells you is
Mel,
the allowed depth.
Mel, we're
Yeah.
gonna have to, we ran out of time, so we're gonna have to cut
Okay.
it off. You guys want to meet together at a hack room, pick one of the hack rooms in the BBB server, and you could continue the conversation. Do you like
Okay.
to do?
Okay.
Thank you.
Okay. Do I go full screen? Here you go. Me again. So the Chromium people came to me, who are not here. Vaibhav Shankar, I think, is listening but not able to talk, and there's other players involved. I'm going to do my best to represent them, but I'm not a domain expert on Chromium. But so, in fact, there's probably people in this room that know more about Chromium than I do. But this is what Plumbers is all about. Okay. Okay. So the opportunity is that today Chromium is being updated to talk to other OSs such as Mac OS and Windows, which have QoS APIs. And they came to me and said, hey, what should we do on Linux? And I said, hey, we don't have an API for that. And what if we did? What good things could we do with it? And so, you know, the idea would be, ideally, they would use the same API for all OSs. Not going to work, but maybe a similar, they do have a separate build for every OS. So, you know, that's not, so, and this is the Chromium people came to me. Thank you very much. And Vaibhav Shankar in particular helped write this presentation. So some context, things I didn't know about Chromium. There's actually a link, if you follow this, you can go to see the patch to Chromium that is changing it. Apparently they used to have a notion of priority, and now they're changing it to thread class, thread type, I should say. Secondly, on your Ubuntu system, the browser, Chromium browser, runs just as a regular process, but on Chrome OS, it does have the opportunity of elevated privileges. Of course, you could elevate the privileges on Ubuntu too, but this is how things are today. I think Vincent already mentioned what the problem is with nice. You know, nice is nice if you know what everybody's doing, but I can't nice myself and have it mean anything, not knowing what everybody else is doing. Real-time classes, extremely powerful. Complexity hurdle, portability challenge, and permission and trust challenge, justified because of the power. It's with great power comes great responsibility. So do you want your Chromium browser to be using real-time classes? Maybe, maybe not. Preemption, as discussed earlier today, also the value proposition for preemption, I think, is unquestioned. In fact, there's probably multiple value propositions for preemption. How complex to make it is maybe something we still have yet to discover, but again, the question is how best to expose that to applications so that we, the kernel, can do the right thing without having to guess. And so from my domain expertise would be, what do we do on hybrid CPUs? If we have some hints, we can decide, oh, this is a task which is, primarily interested in running in the background, and we just run it efficiently, save some energy that you can give to the task that is used for interactive performance. Sched-idle comes in as a possible a mixture in this stew, and that is, one could imagine that, say, a task which we're seeking to run only efficiently would say, hey, please give me Sched-idle. But then you look at Sched-idle and it spreads just like everything else. There's no coalescing, which if you care about efficiency is sort of the opposite of what you want to do. Maybe this is just a bug or a feature that we need to fix, but that's another possible thing on the table. And finally, again, from my area, so there's a number of things in the hardware which we can do per task, which can help differentiate. It's a zero-sum game. Power is zero-sum, performance is zero-sum, and so I think actually Vincent said it earlier. In the face of ignorance, we treat all tasks as if they all want the same thing. They don't all want the same thing, and if we can tell who's the winner, we can say there's a knob, for instance, on Intel processors that says give this guy more frequency than this guy, or on HT, as been discussed many times, you can have a scheduling priority inversion just because the hardware is assuming these two guys are equal. Well, they're not equal, and we can make them unequal if we know. And in fancier chips, there's, cache quality of service, there's memory quality of service, there's a whole bunch of other things. Some chips have simple knobs, some have complex knobs, but right now, we don't know how to plumb that all the way from the user to actually make it easily accessible to the user such that we can take advantage of all those folks. So what does Windows do? And this is a quote, I didn't write this. I guess you can read it as well as I can. I'll just say the bottom line, and that is that Chromium's using what Windows calls the high, medium, low, and echo labels for their tasks. What they do inside the OS, you'll just have to go read the Windows documentation to figure that out, as do I. And this is sort of a summary table. So there is interestingly, there is a notion of a selection may do something on DC and something else on AC, which is interesting, which makes sense. I don't think they used background, but they do use echo. I think, in my experience in this area, the most important thing if you're making classes is to have a high and a low, and then the everybody else. You don't need 21 classes, but it's really important to get the high and the low separated because they really do want totally different things, and then the guys in the middle. So any system that we might come up with, I would vote it's probably at least 3 classes. Let's see. Oh, and then there's a media and a deadline. I don't know that they use the deadline class. Okay, Mac OS has a sort of an analogous system, and the Chrome guys say that they're using what's called background, the lowest, user initiated, which is the highest, and user interactive, which is one step below the highest. I believe that the User initiated are things that like moving your mouse kind of things, and user interactive, I think, are things that you can see. Yeah, immediate results, opening, responsiveness and performance. Nearly instantaneous. Okay, so the second class is nearly instantaneous. So, I mean, this is what an application developer is going to read this table and say, hey, my thread is this. And I think an important observation is that these schemes, the developer, in this case, the Chromium developer, knows what they're creating a thread to do, right? I'm creating, say, a thread to handle media, and I might have a deadline, and I might, or I might be a background task, or maybe I'm a tab that's, I don't know, rendering an advertisement, and so maybe that's not so important. You know, I'll just run, and I wouldn't want to interfere with the interactive response time of the system, let the foreground tab work while the advertisement stalls, or kill that task if I can. But anyway, so they don't actually know anything like nice. They don't know, oh, what's my priority in Linux? They don't know anything about Linux. They don't know anything about Windows. They know about themselves. So I think the solution, that solution is very attractive because it's something that actually is sort of portable. You can build your browser with the notion of these are our background tasks. No matter what OS you're running on, everybody seems to have a concept of background tasks except for us. And they don't need to really know about the OS. They don't need to know about any of the hardware hooks that I know about. We can put that in the kernel and plumb this through perhaps, and these are the other classes. Let me just finish with Apple, though. The nice thing about Apple is they're using pthreads. The not as nice thing is that it's non-portable and it's whatever the ASPL's Apple license. It's not like we can copy that and plumb it. I think that's incompatible with our glibc license. But let's see. Yeah, let me just put in one more thing before I get to sort of solution space. And that is, you know, this is as asked by a Chromium application person, what do they want? They want the ability to run tasks, say on today's CPUs, you know, say a hybrid CPU, they know that they can do media, for example, on the lower performance CPUs and meet deadlines, but they don't know how to ask for that. We don't give them a way to ask for that. Or an easy way to ask for that, and then they have a couple of numbers for their deadlines. So right now what happens is they, you know, an ITMT, say on an Alder Lake, we'll stick them on a P-core, and if they go over a certain amount of utilization, we'll ramp up the frequency. The next thing you know, we're burning much more power, meeting deadlines much sooner than they need to be met.
Yeah, I think, I mean, maybe it's not the...
Take your mask. Yeah, good.
Yeah. It's not the simplest interface, but something like this, you can probably use a deadline.
Yes, absolutely. You could use set schedule deadline if you had the sophistication and if it were portable to two other operating systems.
Yeah, I'm saying that maybe, I mean, it's not the correct interface. I kind of have the impression, I'm not sure. I mean, my impression is that the scheduler, I mean, what we have in Linux probably is already, I mean, we have the features, but we don't have like this level of abstraction.
Well, with sched deadline, you actually have to tell it what the deadline is. You can't just say, hey, sched deadline, because then you've got to say, what is my deadline, right?
I was to say, where do you want to put that at the kernel level? It's look like, I mean, I understand that Chromium would like some things like that, but from a scheduler point of view, what is I want to run fast?
Yeah.
I mean, it's look like we need a kind of matrix between what user space want and how to use the kernel interface right now.
I agree. So this is the ask. This isn't a proposed solution. This is the sort of a problem statement. Let me take a guess at what you're asking, which I think might be something like this. Okay. So what if, I'm just throwing this out there, what if we took you know, our pthreads and we said, great, we're going to have, I don't know, I've got 5 classes on here, and what if we made them sched set adders, and we had a sched set adder QoS hint, right? And then all we've got to decide is, well, that plumbing is actually pretty trivial. And then all we've got to do is say, what are the hints and what the heck do we do with them, right? And so, you know, preemption could be a bit, or it could be a number, or there could be multiple of them. We could, you could actually even override it to make a sched idle class, or you could just play around with the priorities as long as you've got permission to do that, are nice priorities. The one I'm most interested in is the column on the right, because that I can use to hint the hardware to say, great, I don't know anything about your time quantum, but when you're running, I want to treat you this way. I want to treat you that, with maybe very high or very low frequency, or an efficient setting on my frequency, or maybe I want to hint that to run on a specific kind of CPU at a specific operating point.
And my point is that shouldn't it be a library provided? I mean, that can be portable, because even from one laptop to another one, probably the configuration can differ. Android is using something like that. They have this kind of interface. They are putting the top app application in a C group with some feature. They have some system background or some display, and everything is done by the distribution, by Android itself, not by the application has a high-level interface.
What does the library know? What are they putting in the library?
But I don't know the detail. Some people but I mean, they are just translating some application high-level request into C group configuration, CPU set, priority, and so on. And that's it.
Yeah. So say this proposal is actually orthogonal to those knobs. We still have C groups and all their power. This is for when you don't have that, pretty much. But you can also have this and that, because C groups, of course, are used for 100 different things. They're used for partitioning systems into totally into different uses. I don't see the thing about say you said, okay, let's have a background C group, and let's say, okay, let's put all those tasks into the background C group. Well, now I'm the browser writer, and I've got to have somebody put me into that C group, and another OS might not have that, where the whole time I knew I have this background thread. In fact, I've got 5 different kinds of threads, and I've got 200 of them. I know what they are. I can do that. I can ask them myself. I am honestly the most important application on the laptop by a large margin. It's like 90% of our problem. If we get the browser working well, the system's going to work well. So why would I encumber an administrator on to know anything about the hardware? Because the application knows, it gives the hint to the kernel. The kernel's job is to abstract vagaries of the hardware on different platforms. In fact, you could have, like we were talking about earlier, you've got these tables, they tell the kernel about the hardware, and you don't really, I'm not sure that we have to put that in user space.
Typically, coming back on Android, typically each SoC or mobile phone manufacturer will set, for example, for the background that they are using uclump to say background should not run above that, because that's where it's power efficient. Above that, you will waste too much power. And it's only the mobile phone manufacturer that can do that, because from one to another one.
Right, phones are verticals, right? That's a little, yeah.
And they have similar problem to you, or to what you are proposing for Chromium. That's my point. And I'm afraid that if we put that directly at the Linux or kernel interface level, then we will be asked that from one SoC or from one laptop to another one, you will have to change what it's been behind, because on one side, the priority 20 is good for, I don't know, one laptop or Chromebook, but it's not working well for another one, because the SoC is more efficient, because it's faster, and it's really platform dependent.
Yeah, I think, again, I think from my position, it's the kernel's job to hide that from the application. It's not the application's job to tell the kernel about the hardware.
I'm not saying it's at the application, but the application is using some library. I mean, is using glibc, for example, most of the time.
So in this instance, Chrome would say, sorry, I'm here. In this instance, Chrome would say.
Why don't you take your mask off?
I think you can still hear me well. When Chrome would say, hey, this thread is going to be a background thread that I'm spawning. Maybe it's downloading. It'll call into a library. That library will take care of putting it under the background C group. And what the background C group means would be decided by the laptop or Chromebook manufacturer. So Lenovo would say background means use these CPUs with this max frequency, whatnot, but Acer might say something else. I think that's what Vincent is trying to say.
I think that will work fine, but it won't work on Ubuntu if they choose to use C groups for something else that's incompatible.
But I thought you're not trying to solve
But that's a user space problem, really. I mean, what you want to do is to expose the information about the hardware and the properties of the low power cores and the power cores out so that some user space library can make an informed decision what to tune and what to pick. And having all this complexity in the kernel, and then you're going to end up in the kernel with defining what default means, and everybody has 500 different opinions about what default is. And this is not going to work well in the context of the kernel, but you can make it work well if you expose the information and let the user space create some policy around it. Just expose the mechanism and the information, but not do policy in the kernel. I don't think that will work.
I agree with the principle of keeping policy out of the kernel for sure. Absolutely.
I mean, another way to look at this is each of those classes you're defining are literally just C groups, right? You can create how many ever C groups you want for each of those classes.
Yes. You could also take the point of view that you're the scheduler and you've got a head of queue and you could give a damn what C group the next task is, and you can have per task properties that are different than every other task in the system, and all you want to do is go and do that without having to figure out to go into to look at the group he's in. The other problem with C groups is that they're hierarchical, and if you have a per task property, he can run anywhere in the system in any group.
We have a question from Qais, remote.
Yeah, can you hear me?
Yes.
Yes.
Yeah, so actually I wanted to say Japan because we are looking at something similar in Android, and C group interface is useful, to be honest, but it's very aggressive, like in terms of very coarse grain. What we're trying to move to is into like kind of per task API, where like application give a direct hand, and this is actually done in the middleware. So we're trying to do the QS kind of control in the middleware using uclamp. I've shared a link to an API that's currently in Android, I think 12, where the applications can basically give a deadline to the middleware, and then the middleware will, and like every time it finishes its work, it tells the middleware like, hey, I've done. And then that middleware will measure this time and either boost the work or reduce the boost using uclamp min to ensure it's meeting its target deadline. And well, that can be used for also efficiency. And I think at least in some discussion on LKML, Paul from Mozilla was looking to use uclamp max to as well dynamically control the maximum performance point the application can use or the task can use so that it saves power. So there is room to do some work at the middleware, and that's the point I'm trying to say. And it will be nice to have actually something very generic that can be used by any distribution, because the current maybe Android solution is specific to Android programming model. But I'm sure we can extend that concept for other distributions by having a library that does all this QS work.
Great. Who's responsible for that library?
Yeah, I think the community needs to do. I think I'm just agreeing with Thomas over here is that at the kernel level, maybe we need a bit more. I think we are missing some stuff. Like I like that ideas of like spreading versus like packing and latency information. But like with background task or something else, I think that's more suitable for a middleware kind of library that does this work actually.
Yeah,
Because I
just
think
one point. Yeah, sorry, there's like 1 minute left. So you could take this first column, put the information in the kernel associated with every thread, then the rest of that could be configured by user space through SSFS files. I mean, that would solve it, right?
No, that solves nothing because it's too centric on a particular workload, like the Chromebook thing. But if you look at servers, if you look at real-time systems, the left table is just useless. So don't do this to the kernel because this is really policy which is system specific. So it's totally different on a Chromebook. It's totally different on a phone, and it's totally different on a real-time system where you have totally other constraints. But you really want to use the power information as well because we have battery-driven real-time systems too. So please expose the information which is necessary to do an information and have the mechanics to actually into the kernel or put it into C groups or whatever the fancy of the day is.
So I'm hearing that people like C groups because it's easy for them to be administered by somebody.
It's not even without C group. I mean, you can even without C group, you can, if you have a middleware, as Keith was mentioning, between your application and between the application and kernel, you can say, I want this task thread to be this kind.
At the end of the day, when I switch in a task, I need to know what setting to do this set to. Where do I get that?
Exactly. You need a mechanism to attach that information to the task.
Right. I need some per
And
task.
whether that
could be the groupies in, or it could be per task.
could be groups, could be per task, could be whatever. That needs to be sorted out, but provide the mechanism and not map it to policy. Policy is user space.
Last point for Joel. Joel gets the last word.
So about the policy in the kernel, I think your last talk or a couple talks back, you mentioned reading classifying the workload in the kernel. So it
Right.
sounds like this is already a thing, like workload classification. Right?
Yeah, but honestly, we do pass some of that information to user space and where that can be acted on, but for low-level decisions where we can optimize performance by knowing the class. In that case, it's the class of ISA that you're running. It's not my identity as I'm a background task. I could be doing VNI as a background task. That doesn't mean I should be running a high-performance core. They're separate things.
You're right.
Okay, well, it's a good discussion, and it seems like there's more to discuss. Thank you.
Didn't you make slides?
I just.
You said you would do everything. Yeah. Thing working? No. Oops. Technology. I start with that slide everybody forgot, thanks to our sponsors. So we got that point sorted. I can't forget it anymore. And Daniel wanted to put up a slide for me, but yeah, you promised. You promised to take care of everything. So, but it would be only one slide with the word question mark on it. So here we are.
Question mark.
If you don't ask questions, I'm going to ask you questions. Okay.
Is print K gonna be real time?
Oh, that's a tough one.
Is print K gonna be real time?
So the question is more when it will be time for print K. So this is the real not answered question today. So we have ideas on that, but let's see where that goes. At least Linus didn't hate it immediately, so there's a decent chance that we can make progress. Yes, there's a BOF tomorrow afternoon at 3 o'clock where we talk about print K. So further questions about print K are forbidden from now on.
Question mark.
So I know I'm standing between you and the beers, so if you want me to stop, we can agree on that, but you have to pay the beer.
Oh yeah, sure. What's missing? What still needs to get upstream from the
What's missing?
RT patch
Okay. We're back.
Only that?
We're back to that. No, it's actually print K.
Good.
So and a few minor things which only make sense when we put the switch in, and then after that we have the lazy preemption ports, but I'm not going to push them now before we have actually the thing enabled. Because right now I don't want to have that discussion with anyone. It's going to be interesting to get that in, but it's not the end of the world if it's not there at the first place. So we have to fix print K. That's the more interesting one. Once we get if we can agree on the infrastructure and get the infrastructure in, then it's definitely the gates are open for everyone to help on converting the console drivers over. It's going to be quite a feast, but there aren't so many, just a few hundred. It's not dramatic. Did larger things before, so PKL was worse.
From what we have in, is there any optimizations and further things that we can do to make things even better? I don't know if there are optimization margins for things that are already there.
There are quite a couple of things we need to think about, but we need to think about a lot of these things in general in the kernel. One is the whole SoftIRQ problem. There's no real good solution to it, but we are now hitting some of the constraints there, especially in terms of real-time communications based on TSN, where the automation industry really looks into. And here we really get bitten by SoftIRQs. So we have to figure out something, what to do about that. And that might be even in the interest of the networking people, because they are debating their own SoftIRQ design as well. So it's not particularly an RT problem, because SoftIRQs are, it's this big pile. Throw everything into the SoftIRQ and then hope that your work gets done on time. But then you have 500 unrelated items in there and you have to process them all. So I mean, the network people mostly set on XTP, zero copy nowadays, because they want to get the kernel out of the way completely. That's one solution to the problem. Unfortunately, you can't do it with all network cards, and especially the TSN ones. There's a couple of issues um, um, mostly a permission problem. On the TX side, on the ORIC side, that's easy, but the TX side is critical. Because there's no core, there's one cord out there which actually can do that, where we can fully restrict what launch time a user space message buffer can actually be in, but many of the other cores just accept whatever is there, which means you can escape your time slot. Obviously, not a good idea. There's plenty of things to look at. So that's, I think, SoftIRQ is the most urgent one to actually study things.
Wonder if read-write locks and read-write semaphores can be another one. So currently they're not fair with respect to readers and writers. And I was actually wondering, so yeah, reading the code, it's you mentioned, well, I don't know, I think it's you, that scheduling was one of the blockers for actually implementing priority inheritance also for readers. And I was wondering if you
I mean the multiple reader inheritance problem is infinite large, and I mean we had this code and ripped it out again because it was more trouble than it solved.
Yeah. So you mean there is no real fix for it, or because I mean we're basically.
I haven't found out a solution how to do multiple reader inheritance if the writer is stuck. But on the other hand, looking at the use cases where reader-writer locks matter, and they matter, they're not that hot path anymore than they used to be. A lot of the reader-writer locks and the reader-writer semaphores got replaced, especially in the hot path. They all went for RCU and lockless protections.
Yes, well, actually, I'm asking because I actually added kind of recently a read-write, per-CPU read-write semaphore in the scheduler hotpath. Well, it's not a hotpath, it's the set scheduler, because we needed that for scheduling. But I guess, yeah, I guess my question would be, should I go and try to, I don't know, substitute that with a mutex, or I think that might be the question. I mean, the solution.
Let's see what happens.
Yeah.
I mean,
okay.
It's not. I mean, if you want to set your scheduling policy, come on, you can wait. It's not the most urgent thing in the world. It's when your thread starts and when your application boots up. You shouldn't do that every other second.
You shouldn't. But yeah, okay.
And especially not in your highest priority thread. I mean, you can do so many stupid things in your high priorities or in your deadline thread, which make your you miss the deadline or blow your latency out of the window. So don't do that.
Yep.
I mean, we can't make an OS which prevents people from being stupid. That's
and I'm glad that he doesn't know.
measures against stupidity do not exist, at least no legal ones.
And I'm glad you don't know why we have that problem. It would be worse. Questions?
Just a quick note on the same topic. ePOL is currently broken.
What?
ePOL, event poll.
ePOL?
Yeah.
Why?
Because of the fairness and it's using the read-write lock. It's been reported, it's been discussed. One of the proposed solutions is just use RCU like with the other users. But it doesn't fly so easily, so it's still one of the open problems. And since you were mentioning read-write locks, I don't know if there are any more serious users, but ePOL is having ePOL broken is not nice.
No, I mean it's not broken. It's not less deterministic than. No, there's no good solution for it. But I mean, there's basically two options you have. Either you accept the right starvation, or you go for a single reader. We had that, didn't scale well, caused other problems. So yes, I mean, we have to look at the EPOL case. I don't know. Yes. I mean, most of the other reader-writer-lock problems are pretty much, there's not much happening on that side that people report issues. So I saw the EPOL thing fly by. Yes, the non-RT fairness-based reader-writer-locks are really nicely solving the problem there. But it's not entirely clear what we can do on the RT side. What we could do, and I was experimenting with that years ago, but it went into complexity explosion land, was basically once the writer is stuck, do not allow more readers to go in. Well, that's a slippery slope too, because I ended up with other priority inversion issues which I didn't see before. Yeah, that's an interesting one. Get rid of reader-writer-locks. Don't use EPOL.
Isn't the main excuse for reader-writer locks the task list? So once we kill task list, we can kill reader-writer locks.
Oh yes, task lists.
But that's another mission impossible. But Linus, the only reason he doesn't tear it out, at least in the past, was like basically the task list.
I mean, if there are no more users, we can rip it out. Then, I think there's some people working on replacing tasklets because, at least on the usage sides, because many of the tasklets are outright stupid.
No. I mean the task list.
At the task list.
Yeah, not tasklet.
No, task
I'm
list.
also removing tasklets, but yeah, the task list is the main
No,
user.
task list lock is interesting.
Exactly.
I think there's a few more reader-writer locks than just that one. I might be wrong.
I'm sure there are. It's just like
I mean,
the main.
there's the reader,
the main user.
there's the semaphore, which is being worked on for other reasons because it doesn't scale.
There's been a few sessions in this conference about that.
Yes. So I mean, and there were several attempts already over the past 10 years to get rid of it, or at least to rip it apart. I don't know what the current state of affairs is.
We have 3 different patch series attacking different aspects of the problem. Maybe we'll get something that people are willing to accept. We'll see.
So maybe they throw them all together.
They are not mutually exclusive necessarily, although I'm sure merging will be fun. One of them is, the most recent one is Seren, whose last name I'm not going to try to pronounce, Seren B from Google. And what they did was they take and they focus the locking on the VMA. But they kind of cheat. They acquire a lock and set a bit saying this thing can't be moved. So it's not really a lock, but it's a thing that protects it. Okay.
Protects per VMA.
Yes. And they got some pretty impressive speed ups out of that. They don't get as much as you get by using SPF, but they get like 70, I want to say 70%, but I'm probably wrong. Okay.
Yeah.
Another one is Mapletree. Mapletree, even without RFC protection, gets some benefit just because the layout is better. It's a better data structure for that sort of thing. It turns out you have to RCUify the VMAs to make Seren stuff work because you have to get a lock on the VMA and it.
Right.
Yeah. So
you could protect the VMA list with
that's a potential first step. Assuming that that's accepted, that's a potential first step that would help the Mapletree deal with some of that, I think. But talk to Liam and Matthew to be sure. And the third one is something Peter started, as you said, in 2010. Laurent Dufour took it over some years after that, and now Michel Lipinès is working on it, and that's the speculative page fault path.
Right.
Where you use RCU to protect the page fault stuff and retry, kind of like Dcache entry, sort of. So those are not mutually exclusive. Hopefully, at least one of them gets in. Hopefully, they all get in, as far as I'm concerned. And beyond that point, if we can RCUify the page structures like PowerPC already does, then that gets rid of some weird garbage we've got where monitoring can stall servers. You asked, you won't make that mistake again.
Yeah, I'm not complaining.
Give me time, give me time. Oh.
Any other questions?
So what's the status of using eBPF on pre-M30 kernels?
I haven't heard complaints since I fixed the BPF back then. I don't know. I haven't heard anyone complaining that it broke again. Bastian, do you know anything about BPF? It's awesome. Of course it's awesome. It's the most important invention since sliced bread.
I've been using eBPF with RT, and there's no visible problem.
You didn't make it explode?
No, maybe my fault.
You didn't try hard enough. Okay, BPF, we had that one. So what else is interesting?
I guess there's this problem of priority inversion in CFS, and if we can, use some of the same logic that we use for RT mutex, but for CFS to, so it's not exactly priority inversion because in CFS everything makes progress, right? But it's more like forward progress. So important things slow down and not so important things run, like, and they
You're
block
talking
on
about lock contention?
Yeah, a lock based.
Yeah,
so it's a real problem. It's
Yeah.
come up a number of times.
I mean, in the
Runtime inheritance.
in the early days of RT, where we actually had to make sure that the PI code is very much exposed. We used to do PI on SCADA 2, but I think we dropped that over time because it was just too expensive. We could bring that back, but that brings me to a different question. What's the state of proxy execution? Oh yeah.
Yeah, I think we have people interested in bringing forward. I personally didn't have time, but it's probably gonna move forward. I spent time on it. He spent time on it, but then yeah.
Yeah, no, a lot of people spend time on it.
But I think that if you have like a CFS, giving the proxy to the other, I don't see it increasing the amount of runtime that task will earn. You inherit the scheduling entity. I think the idea that they would like to have is like summing up the runtime that they could use, so the task that owns the lock would have more time to run.
Yeah.
So it should be summing, not inheriting.
That was something I was looking at as well, to have a kind of taking the nice priority of the one that is waiting. Right now, if you have priority 19, and you have a log that someone else is waiting for, you will run 1% of the CPU.
So,
whereas you can increase
but
that.
what are you waiting on a concurrency control, or you're just waiting for something to finish?
something to finish.
Something to finish.
Yeah. Yeah.
Yes,
Yeah.
inheriting nice would help, but you need an interface to do so, because you have to tell someone that you're waiting on somebody else.
Yeah, yeah, yeah. Yeah, yeah. Maybe I was thinking of, because in RT mutex right now, we are checking if a RT task is waiting. But you can be in a situation, oh, I don't know. If your RT task is waiting on a CFS task that is waiting for another one, the priority is inherited on the older level? Yeah.
So
Okay.
if it's
But nice inheritance doesn't really work.
always inheriting through the full chain.
Okay. Good.
With a preemptor, that is when.
No, even on use priority inheritance mutex mutex on mainline, then you inherit throughout too. But fun.
Yeah, so nice inheritance doesn't work, and it's instantly broken by C groups. It was mentioned earlier, what you need is a sum of weights in the whole weight tree. And that's a bit more tricky to do.
Could you repeat, Peter?
Nice inheritance doesn't work. Wait.
We got that part. And the next
Right.
one?
So nice inheritance is also instantly broken by C group hierarchy. And what would be the correct thing to do is to sum the weights in the entire weight tree.
Sum up the weight in the weight tree.
Yeah, so it's summing up things, not inheriting.
No.
It's
Correct.
summing up time to be expended, yeah.
No, I just came to my mind because we were talking about it. What's the state of the whole proxy execution thing? Because that would really be nice to have. Yeah. You have to get out of your hidey hole and do something useful again. Well, you know, everybody hides somewhere and pretends that he's doing important stuff while neglecting the real important things. I need to talk to your manager.
Good, we have 4 more minutes. We can spend in silence. We can say thank you. We can questions.
Oh, we can.
We can
thank our sponsors.
Thank our sponsors.
Okay, with that, if there are no more questions, thank you for attending. Thank you for staying around, and have a nice evening. If you want to know about the print case saga in detail, it's tomorrow, 3 o'clock.